right, it says we're live. I'm just waiting for confirmation here that everything's working. We're doing January 2020. The link should be in the description box. How long is my delay here? I believe it's 30 seconds. Okay, anyways, we're doing January 2020. Looks like everything's working. Okay, as we run through this, of course, feel free to ask questions. I will refer you to some videos on this channel if that is needed. I'm kind of trying to work dual screen here. My thing doesn't want to work. Oh, come on. Can I shrink this window? No, I have to grow this window. Got it. Okay. Let's get right into it. We're going to start with number 1, part A. Okay, jumping straight into it. Which statement describes a concept included in the wave mechanical model of the atom? The wave mechanical model is the most recent model of the atom, and that is going to be the one where you have a nucleus, you still have protons and neutrons, obviously, but instead of the electrons being in distinct, like, circular orbits, they're in these weird, fluffy clouds of probability. And really what that means is that the electron doesn't do a perfect circle around the nucleus. It kind of like wiggles and wobbles around the nucleus. So the orbit is kind of just like, it's probably in this space. And there's like a path that it follows, but it can veer off that path a little bit. The pictures of it are definitely going to describe it better than I ever could. Picture's worth 1,000 words. So protons, neutrons, and electrons in the nucleus, heck to the no. Electrons have never been in the nucleus of anybody's atomic model. Electrons orbit the nucleus at fixed distances. That is going to be the Bohr representation, so that's the one that comes just before this one. Hard indivisible spheres is a no. And then we have, they are located in regions called orbitals. That is going to be it. Actually, at fixed distances. I don't love this question. Already, I'm not in love with this. Fixed distances implies that it's like a perfect circle, right? Because it's a fixed distance. They are in regions. I would argue that those regions are not called orbitals, they're called clouds. But January 2020. So if there's a question that's like really crappy, the chemistry teachers of New York State do write to the Regents Board and they make a bunch of complaints. And if there's enough complaints, they will go back and say, like, oh yeah, we probably shouldn't have counted that, or oh, this answer choice makes the question weird. And if you feel that way about a question, you should talk to your chemistry teacher about it. I don't love this. Orbits to me is Bohr, and clouds to me is wave mechanical, but it's the regions versus the fixed distance is going to be what decides this question. Already coming in hot, 2020. Okay. Question 2. As an electron in an atom moves from higher energy state to lower energy state, the atom is going to release energy. Becoming an ion would mean that the electron either has to come into an atom or it has to leave an atom. That's the only way. It moving around within does not make it an ion. So those are out. It absorbs energy, and when you heat it up or when you electrocute it, that's the flame test. When that happens, it means that the energy added is going to help the electron to jump up and overcome the attraction it has for the nucleus. So positive and negative attract, obviously, right? Give that electron enough energy and it goes, oh, I don't care about that attraction. I'm going to jump up to a higher energy level. It'll release energy when it comes back down. This is a very commonly missed question with students. Release, come down, and absorb to go up. Okay, question 3. Two atoms that are different isotopes of the same element. Okay, they are the same element, so obviously they have to have the same number of protons, because if they didn't, they wouldn't be the same element. So choices 3 and 4 are out. They can't have a different number of protons. And they are different isotopes of the same element, so they must have a different number of neutrons. The example here is going to be like carbon 12 and carbon 14. They're both carbon, so they both have 6 protons. One of them has 6 neutrons and the other one has 8 neutrons. The 12 and the 14 are called the mass number. Mass number is the sum of protons and neutrons. And if you're subtracting 6 from both of those, you'll be left with a number of neutrons, giving you 6 and 8 respectively. Okay, question 4 is a periodic table question. And we're going to take a look at that. Let's rotate this so we can take a good look. The elements in group 14, nobody cares, Cammy. 14 is right there, headed with carbon. And period 3, I'm actually going to blow this up a little bit. Group 14 and period 3. Let's take a look at that. This is kind of like just Battleship. You just crisscross them. Like, you got 14 right here, and period 3 is over here, and where those two converge is going to be silicon, which is Si. And you can see that silicon right here is touching 2 sides of that staircase line. Any element that touches the staircase line 2 times, like an edge and a top or bottom, that is going to be a metalloid. The only one that does not follow that rule is aluminum. Aluminum, I hope you know, is a metal. So we're talking about silicon, and silicon is a metalloid. Group 15, I'm sorry, question 5. I don't know where my brain just went right there. Which element has chemical properties that are most similar to potassium? Oh, there goes my washing machine downstairs. I swear that thing is like about to launch into space. Anybody need a job? Engineer that. Okay, potassium is K, and that is number 19 right here. And we're asked which one has properties most similar. The things that are going to have properties most similar are going to be in the same vertical column or group of the periodic table. So the correct answers would be lithium, sodium, rubidium, cesium, or francium. And the choice here is going to be cesium. Calcium is a wrong answer. They're just in the same period. The only thing that's the same about them is the number of electron shells that they have. And then nitrogen and sulfur are nonmetals, and they're all the way on the other side of the table. But I'm going to tell you right here, right now, the reason they did nitrogen and sulfur is because they wanted to trick you thinking that P was potassium. It's phosphorus. So be very mindful of that, because they do try to trick you. Because the Regents Board does not. Does not love you. They're here to test you. I mean, that is kind of the point, right? But also, like, don't be mean about it. Number 6, which element requires the least amount of energy to remove the most loosely held electron from a gaseous atom in the ground state? That right there is the definition of ionization energy. So they're asking which of these listed elements has the lowest ionization energy. And there's 2 ways to do this. One of them is easier than the other. I don't know why I can't get this to scroll over. Like, I just want to move. Nope. I just want to move. Why are you being annoying? No, thank you. Please move over there. Stop doing that. Stop doing that. Shrink that. Okay. Sorry. My goodness, I don't like Cammy. So there's 2 ways to do this. We're gonna do the easier way first. The easier way is to just look all of these up on table S. So you go through, you find that first ionization energy, and compare all the numbers. That one's a little bit more time consuming. Some of us are really like with it with the periodic table trends. I am one of those people. Surprise, surprise, the chemistry teacher knows the periodic table really well. So ionization energy is going to be the lowest in metals, and specifically it's going to be lowest in big metals. That's because big atoms have their valence electrons far away from their nucleus, and metals are trying to lose electrons. So if I'm trying to get an electron away from an atom, I want it to be taken away from a metal, or a giant metal at that, because it's going to be really easy. So out of all of these listed, we are looking at elements that are all in the same period. We are asked about sodium, phosphorus, chlorine, and argon. And the lowest ionization energy is going to come from sodium, because sodium's trying to get rid of electrons. So taking an electron away from sodium is going to be quite easy, because sodium's trying to get rid of that electron. Number 7 is mostly just vocabulary, which we love to see. Which term identifies 2 different categories of compounds? This is specifically compounds, not formulas, which is why empirical is booted out. Empirical formulas, there's no such thing as an empirical compound. So that is out, and that is out. Ionic compounds do exist, so that's fine. But here's the thing, covalent is not a compound type. It is a bond type, and things that have covalent bonds are actually called molecular compounds. So this question to me is like silly and kind of mean, but it is a fair question, technically. So that would be choice 3. And if you've been watching these, you know my tablet is so annoying. The tablet is smaller than the computer screen, so I kind of get caught on the edges sometimes. Okay, question 8. Which statement describes the energy and bonding changes as 2 atoms of fluorine become a molecule of fluorine? If I were taking this test, I would write this equation so that I could see it and kind of get a feel for what was going on. 2 atoms of chlorine are going to bond and form a fluorine molecule, so that it would be F2. Molecule means that they're bonded. And this is BARF. And I think that this has come up on every test that we have done on this live stream. BARF. BARF is a gross acronym. It is actually break, absorb, release, form. When bonds are broken, energy is absorbed. When bonds are formed, energy is released. And in this case of F and F becoming F2, they are obviously forming a bond. They're bonding to each other. So they are going to release energy. So a bond is formed and energy is released is choice 4. Number 9, which part of a calcium atom in the ground state is represented by the dots in a Lewis dot diagram? Okay. This really is just like, what's the definition of a Lewis dot diagram? Lewis dot diagrams are going to show the atomic symbol. So in this case, it would be Ca. And it's going to show valence electrons as dots. Electrons in the first shell are not valence electrons. It's not showing us protons or neutrons. It's just the valence electrons. And for calcium, those happen to be in the 4th shell. If we go look, that's what it should look like. If we go look at the periodic table for calcium, I'm going to zoom in as much as I can get on calcium here. Okay, calcium is right here. Calcium's electron configuration is 2882. That is indicating that we have 4 rings, layers, orbits of electrons, because there's 4 digits there. There are 2 electrons in the first shell, 8 in the second, 8 in the third, and 2 in the 4th. The number of digits is the number of energy levels. Also, it's in period 4, which means it has 4 energy levels. Okay. So that was 9. Moving to 10. 10 is fantastic because it tells us exactly where to look. It says, based on table S, An atom of which element has the strongest attraction for electrons in a bond? And that is just the definition of electronegativity. Negativity. Electronegativity is when one atom is bonded to another. They're sharing those electrons, and it's how, like, unfairly they're trying to share that electron. The higher electronegativity means that that atom is kind of hogging the electron and not sharing it very nicely. So we could look up all of these on table S. That would be just fine to do. You just look them up. Electronegativity is right here. It runs on a scale of 0 to 4. Nobody has an electronegativity of 0. The noble gases don't have electronegativity values because they don't bond, because they're inert. But other than, go away. Nobody asked you for that. I'm on my husband's computer, so I don't know what half this stuff is. Okay. When it comes to electronegativity and the periodic table trend, fluorine has the highest electronegativity, which is right here. And the atoms that are closest to fluorine on the periodic table are the ones that are going to have high electronegativities. Francium, on the other hand, in the bottom right corner, is going to have a very low electronegativity. So just in general, metals don't have high electronegativities because they're not sharing. They don't have a desire for electrons either. They're looking to get rid of electrons. And then we're left with chlorine and sulfur. Chlorine is right next to fluorine and sulfur's over here. If we go and look them up, they're 16 and 17. They are 2.6 and 3.2. So following the trend, chlorine does have the strongest attraction for electrons in a bond. Moving to number 11, which substance cannot be broken down by chemical means? Really what they're asking you is which one is an element, because that's what an element is. It's a substance that can't be broken down by chemical means. And there's a few ways to kind of figure this one out. The first is which one of these appears on the periodic table. So you should get aluminum. Aluminum is Al. Now, ammonia is the common name of NH3, which I hope at this point in the year you know that. It's a super common compound that we talk about a lot. Aluminum oxide is Al2O3. And then ammonium chloride, is NH4Cl. And if you look at all of these, they have 3 capital letters or more in their formulas. I'm sorry, they have 2 capital letters or more in their formulas. And that means that they are compounds. 2 capital letters would indicate that you are working with at least 2 elements. And if you have more than 1 element, then you have to, at minimum, be a compound, though you could be a mixture. Okay, for question 12, which statement describes the particles of an ideal gas based on kinetic molecular theory? There are a few rules to kinetic molecular theory, and kind of you just have to memorize them. It's really annoying. What are they? Gas particles move in random straight line motion. They do not experience intermolecular forces of attraction or repulsion. The space between particles is very, very great, and therefore the volume of the individual particles is considered negligible, or in other words, ignorable. Gases are compressible. And there's definitely more, I just don't remember. So the kinetic molecular theory does not allow for attractive forces between particles. The particles move in random constant straight line motion, so it can't be that one. Oh, collisions, that was it. The collisions between the particles reduce the total energy of the gas. No, they have elastic collisions, which means that, let's just say we have 2 particles of a gas and they're going to collide. One of them has 100 joules of energy and the other has 50 joules of energy. When they crash into each other, they're going to leave the collision with 75 each. They split the difference. So even though a particle may gain or lose energy, the entire system is going to keep the same amount of energy. It doesn't lose anything. So that one is not the answer because we're not reducing the total energy. So that leaves us with number 4, which is the correct answer. The volume of gas particles themselves we ignore because gases take up their entire container. So we just count the container as the volume of the gas. Ooh, 13. What a trick. Okay. For the part A questions, I don't want to say that there's a rule anywhere written down because if there is, I have never seen it. But in all of my years of taking Regents exams, there has never, ever, ever been an exam where you are taking out the calculator in part A. So if you're tempted to take out the calculator in part A, I urge you to reread the question. Because 13 is one of those that I'm sure is going to trick a bunch of kids. What is the amount of heat released by 1 gram of liquid water at 0 degrees Celsius when it changes from 1 gram of ice at 0 degrees Celsius? This is really the definition of heat of fusion. When you are melting stuff, you are talking about specifically the heat of fusion. So if you didn't know this, a math-brained kid could figure this out. Using table B. The heat of fusion, you'd have to know that it's for freezing and melting stuff. Specifically, we're talking about water. The units here are joules per gram. So that means that it is going to take 334 joules of energy to melt 1 gram of water at 0 Celsius, at its melting point. Or you have to release 334 joules per gram of water at 0 Celsius in order to melt a sample. So because we are talking about 1 gram of water at its freezing point / melting point, they're the same temperature, and we're talking about water, that is going to be 334 joules per gram. Again, this is one of those that looks like it would be a math question, but it's part A, so definitely just check it over. If you wanted to, you could do the math here. You're going to come up with the same answer. You would do Q equals MHF. This pen is very bold right now. Hold up. You would do Q equals MHF. Q is the amount of heat, so that's the question. We're going to leave that. The mass is 1 gram, and then the heat of fusion is 334. So technically, you don't have to do any math for that. It's just a concept question, but if you wanted to, you could. But again, you shouldn't need a calculator for part A. You shouldn't even, like, count on your fingers for part A. It should just be vocabulary and reference tables. Question 14, which term identifies a type of intermolecular force? This is just vocab, which could be great, could be terrible. It kind of depends on where you are at this point in the year. Covalent bonding is a type of bond. Oh, I hate this question. No, I don't. I actually like this question. Covalent bonding, you know, is when they share electrons. It's a bond. Ionic bonding is when they transfer electrons. That's a bond. Metallic bonding is when metals, like in a chunk, let's just say we have like a big brick of gold sitting on the table because I'm a queen, and one gold atom is going to toss its valence electron to the next gold atom, and the gold atom beside that one just hot potatoed its electron into me, the gold atom. So they just like hot potato these electrons on and on and on and on and on because they're constantly trying to lose electrons. And because the electrons are moving, that's going to make the metal shiny. That's why metals are conductive. That's why they're malleable, for all of those reasons. So that is technically a type of bond, even though it's just a bunch of gold atoms sitting together. But hydrogen bonding is a super strong intermolecular force. Whoever named it thought it was because of bonding, but it turns out that that's not true. It's a force. So you would have something like H2O And what happens is that this is a polar molecule. This is the Lewis structure for water. Always draw it at a right angle because it'll help you to remember that it's polar. So we have water here, and this oxygen, this area is very negative, this area is very positive. And what happens is that that oxygen will kind of like move through space, and because it has that big negative on it, it will be attracted to positives out in the world, either positive ions, or it could be other water molecules because it has that positive region there. And that is part of the reason why water like sticks to stuff. It'll stick to your body. It takes a long time to evaporate. All that is because of water being polar. And then those water molecules just hang out with each other. It is a dipole-dipole force, but it was so strong and so different from a dipole-dipole force that it had to get a new name. And specifically, hydrogen bonds occur if there is a hydrogen on the molecule that is bonded to a Fon element. So that would be fluorine, oxygen, or nitrogen, any of those. And if you take a look at the periodic table, those three elements are together, and that's not a coincidence. These are your hydrogen bonding elements, Nuff or Fun. That is because they have a high electronegativity compared to their radius. So that is why they participate in hydrogen bonding. There's certainly a video on that on this channel if you need help beyond what I just explained. 15, which statement describes a reaction at equilibrium? This is just the definition of equilibrium. There are 3 types of equilibrium. We do chemical equilibrium, which is a literal chemical reaction. Then there's phase equilibrium for substances just kind of chilling at their melting point, boiling point, freezing point, whatever. And then we have solution equilibrium, which occurs in saturated solutions. But here specifically we're asked about chemical reaction equilibrium. And oh, my dog is definitely freaking out right now because my washing machine is going to take off into space. The mass has nothing to do with anything. Entropy has nothing to do with anything. Rate of formation of the products must be equal to the rate of formation of the reactants. That is true. And the number of moles of the reactants must be equal to the number of moles of the products. That is also a no. So in a chemical equilibrium, the rate of the forward has to be equal to the rate of the reverse. And if that is true, then concentrations or number of moles would remain constant. They don't have to be equal to each other. It's just that if this is 2 molar and this is 5 molar, it's going to stay 2 and 5 because one of the reactions is not overpowering the other. Okay, 16 is the definition of entropy. Entropy is a measure of disorder in a system. We also will describe it as chaos. High entropy things are gases, things at high temperatures, things with high concentrations, like a high molarity. And then low entropy would be solids, cold stuff. High pressure situations, because you squeeze all the particles together, it's more organized. $17, I think this question has come up on every single test that we've done, just the phrasing is a tiny bit different. Systems in nature tend to undergo changes that will result in low energy and high entropy. So to answer this one, it would be low energy and greater randomness. They just changed the word so that they could reuse the same question every year. Think of you, maybe me. We tend to just throw dirty clothes on the floor and not put them in the hamper. That's because we're too lazy to take the extra 5 steps to the hamper, and that results in us being messy. You are a part of nature. That's why that happens. It's not because you're a broken person. We're just part of nature. It's the way that it works. even if you think of like the woods, like nature, trees and things, they are all going to grow like tangled roots, and they're not growing in ways that are super organized. And that is how nature operates. This is something that is, I would bet $30 that it's going to be a question on the test. In some way, shape, or form, they will probably ask this question. Ooh, we love question 18 because it's exactly a reference table question. It says, which organic prefix is matched with the number of carbon atoms that it represents? We love, love, love this because we know exactly where to look, and that is table P. P for prefix. I don't think that was done on purpose, but I love it. And then right here, we just look it up. Hept is 7. That it would be the correct answer. Right there, spitting you in the face. It's just a matter of knowing to look there. I would bet that the most common wrong answer is propan 4. Because prop and but people get confused a lot. So that's that. 19, which two terms represent types of organic reactions? Sublimation and deposition are conversions from solid to gas and gas to solid. Those are phase changes, so that's not it. Sublimation is a phase change, so that can't be the correct answer. Same with deposition in choice 3. But saponification is the reaction where you take a fat and you turn it into soap using a base. And if you look here, sapo, if you just rearrange those letters, that's soap. So that's a way to help you remember. And fermentation is taking sugar and turning it into alcohol. That is how like wine and beer and liquor are made, but also that's the reaction that turns the sugar in bread into alcohol, which like evaporates, and then you get fluffy bread. That's also a fermentation. Question 20. Ooh, this is a great question too, because this also comes from the reference table. I also want you to notice as you're taking this test that like 19, 18, 19, and 20 are all organic questions, so it kind of like gives you an idea of how you should be answering the questions. Just be mindful of that. They do kind of go in some type of order. You probably learned organic towards the end of the year. There are a few teachers who do it in the bonding unit, and I respectfully disagree with that choice, but some of them will do it then. It's usually teachers who love organic. Given the organic functional group C double bonded OH, which class of organic compounds has molecules with this functional group? Functional groups are on table R. Yes. R in all of these cases just stands for the rest of the carbon chain. And specifically here, we're looking at this piece, which is an aldehyde. Aldehydes have that double bonded O on the end of the molecule, so it's always on carbon 1. The ketone is similar, but the ketone puts that double bonded O on any of the interior carbons. Organic acids have an OH, right? You have the double bonded O right here, but you also have the OH. And then esters have 2 oxygens. You have the double bonded O, but then you have an interrupting O as well. I have an entire video on how to name these molecules if you need help with that. Otherwise, if you just become really, really good at reading this reference table, you can pretty much name anything. Okay, 21 asks which particles are transferred during a redox reaction. Redox is all about electrons. Neutrons are never transferred. Positrons are never transferred. Atoms, we could consider maybe they would be transferred, but they're not for redox reactions. It's all about electrons. Right? It's about like conducting electricity, and electricity is just electrons moving through a wire. 22, which process can be represented by a half reaction equation? I'm hoping that this question being sandwiched between this one and this one would tell you, hey, it's a redox question. Distillation is changing, or rather separating, homogeneous liquids. Maybe think of like alcohol and water. You separate them by their boiling point. Sublimation, we saw this earlier on the test. That is going from solid, skipping over liquid and going to gas. Then we have vaporization, which is liquid to gas, another phase change. So we are left with oxidation as the only choice, which is correct. 23, which form of energy is converted to electrical energy in a voltaic cell? That is chemical. The reason a battery works is because of the particular chemicals that are inside of it. You can't just put like oxygen and carbon inside a battery and expect that to work. It is specifically like, hey, I chose this metal and that metal and put them in solutions in order to get the battery to work. Mechanical energy is more like a physics answer. That is the sum of potential and kinetic energy. Nuclear could be a battery. You could do a nuclear battery, but that would be converting not in a voltaic cell. That would be like in a nuclear battery. It would be a whole different device. And then thermal energy is heat. '24 is a really, really, really great question to have for practice so that you don't get tricked tomorrow when you take the test. Which compound is an Arrhenius base? Okay. I hope you know that the answer is 3, calcium hydroxide. But I'm going to tell you the most common wrong answer is going to be 4. And that is because of this OH on the back. COOH together makes this an organic acid. And specifically, when I teach acid base, I tell my students that acids are covalent and bases have to be ionic. And if you look at it this way, that organic acid doesn't trip you up anymore because the calcium hydroxide obviously is basic. It's calcium bonded to hydroxide ion, and they're going to trade electrons. But the CH3, COOH, has no metal. So we're going to assume there that there's only a sharing of electrons between all of those carbons, oxygens, and hydrogens, which would make it covalent. Just because it's covalent doesn't mean that it's an acid, but if it is an acid, it must be covalent. And because that's covalent, it couldn't possibly be a base. Also, if you look this up on table R, the COOH, where are we? COOH right there. It's that little H that pops off, and then the negative ion is the COO with the negative sign attached to whatever the rest of the carbon chain was. All right, moving right along. In a neutralization reaction, an aqueous solution of an Arrhenius acid reacts with an aqueous solution of an Arrhenius base to produce salt and water. Those are the products of every neutralization reaction. And I will show you. We will have something like, let's do HBr, hydrobromic acid, and let's react that with sodium hydroxide. They're going to do the double replacement. H is going to pair up with OH, which is going to give us HOH, which is how I like to write it, but properly you would write H2O. And then that is going to pair up with the sodium bromide. And at this point, I hope you know that salt is just a general term for anything that is ionic. So that is why neutralizations are always going to give you salt, meaning anything ionic, and water. 26, when they always refer to Bronsted-Lowry acid-base theory as one acid-base theory. I don't know why, but they do. This is going to be related to the prefix bad. with 2 A's. And this is that bases accept and acids donate. And what this is in reference to is protons or H+. So bases are going to be H+ or hydrogen ion acceptors. They accept hydrogens. So if we look at NH3 and we're dissolving that in water, what will happen is that the NH3 will become NH4 because it took a hydrogen from the oxygen, leaving that from the water, leaving that as a hydroxide. So that NH4 with a plus sign has accepted the hydrogen, the H+, that's how it got the plus and the extra H. That's why NH3 is a base. Based on table N, good to know here because it's really going to guide the answers, uranium-238 and 235 have different blank. Okay. The number of protons is absolutely no. They both are uranium, so they both have 92 protons. You could also look that up on the periodic table. I just don't need to because I'm pretty good at chemistry. Uranium also has 92 electrons because it's uranium and it's an atom. If it wasn't an atom, it would have to have some type of charge. Obviously, then it would be an ion. Now, my guess is that they have different half-lives in the same decay mode, but because I'm not that great at nuclear, I'm going to go look it up on table N. I'm good at nuclear. I just don't have this kind of stuff memorized. Okay, so right down here at the bottom of table N, we are looking at uranium-235 and 238. Oh boy. And they both have the alpha as their decay mode. So like I estimated, they had the same decay mode, but different half-lives. 235 is times 10 to the 8th, and 238 is times 10 to the 9th. So they have different half-lives, but the same decay mode. Another thing, number of protons and number of electrons you weren't going to find on table N, so that's kind of why I liked that they gave you that little blurb. 28, a change in the nucleus of an atom that converts the atom from one element to another element is called oxidation reduction. Is related to transfer of electrons. So that's not it. Single replacement is this general format where you're going to steal. There's two outcomes here. If A is positive, like a metal, then you would have AC plus B. But if A is a non-metal and it's negative, then you would have BA plus C. So those are the options for the single replacement. Substitution is organic, where you would swap out like one chlorine for a bromine. Typically it's a hydrogen and then like a halogen. The transmutation is the one where we're going to mutate. We're changing from one thing to another. 29, which radioactive emission has the greatest penetrating power but the least ionizing power? Okay, the greatest penetrating power is going to be the one that is the smallest. Because if it has a tiny mass, then it can fit in between atoms and get really far through like metal and aluminum and cement, that kind of stuff. So if we look at the reference table, the one with the lowest mass, greatest penetrating power, is going to be that gamma radiation or the gamma ray. Positrons and beta are roughly the same size. So they are going to have the same penetrating power. And then the alpha particle is massive. It's got an atomic, or rather a mass number of 4. It is huge. It's 2 protons and 2 neutrons. It's huge compared to the other radioactive decay modes. It's very small compared to plenty of other things. But the alpha, because it's so massive, means that like it gets stopped by the atoms in a sheet of paper. Okay, last in this part A is question 30. Which statement describes a benefit of using fission reactions? Fission reactions are the ones where you have like a really big element. Let's say we have uranium. We're going to launch a tiny little neutron at it, and then it's going to break apart into like barium and strontium and then maybe some other neutrons. And it just kind of like chain reactions over and over again. So first off, we're talking about a benefit. So the answer choice that we choose should probably be a good thing. Radioactive waste must be stored for long periods of time. To me, sounds like a negative. Nuclear fuel consists of stable isotopes. That might be true. I don't know. That doesn't make sense. If it's a nuclear fuel, it should have unstable nuclear isotopes, but okay. Number 3, gamma radiation is produced. That's typically a bad thing. Gamma radiation is not good for us. It very easily mutates our DNA. And then we have large amounts of energy are produced per mole of reactant. That's why we like it. If you have a tiny amount of nuclear matter, like irradiated matter or radioactive matter, you can turn that into a heck of a lot of energy, and that's the benefit, is that you don't need a lot of fuel. And that is everything for part A. So now we will move on to B2. Of course, if you have any questions at all, of course, leave them in the comments because I'm watching for questions. Okay, question B1, 31. Given the table representing the subatomic particles in 4 different atoms, which atom has a mass of 12U? 12U really means 12 atomic mass units, and this is going to be based on protons plus neutrons. Electrons don't count when we talk about mass, specifically like mass numbers, and that is simply because electrons are so tiny compared to protons and neutrons, so we don't consider them when we do masses. In physics, you will consider the mass of electrons because it matters, but here they're just so tiny. So we want the sum of the protons and neutrons to give us 12, and that is going to be 5 and 7. So that would be isotope E is the one that has a mass of 12 atomic mass units. 32, which electron configuration could represent electrons in an atom of sodium in an excited state? We're going to check out sodium on the periodic table. Sodium is over here, number 11. Its configuration is 281. That is the ground state configuration. Periodic table only gives ground state configuration, so 281 is the wrong answer because it's ground state and we need excited. Ground state is when all the electrons are where they're supposed to be, and excited is when you've added a little bit of energy and the electrons jump up. We are looking for a case where electrons left a lower level and jumped to a higher level, but did not leave the atom, because then it's just an ion. So in choice 1, we have lost an electron, because sodium is supposed to have 11 in total, and this only has 10, so that's not the answer. Again, in choice 3, we have just lost an electron. The electron from level 2, there was an 8 right there, now it's 7. That just disappeared, so we're missing an electron there. The correct answer is going to be 272, and that's because the electron left level 2 and went to level 3. So we would subtract 1 from there and add it over there, and that's going to give us 272. Oh, I love this. What is the number of valence electrons in a nitrogen atom in the ground state? Nitrogen is right here on the periodic table. Its configuration is 2-5, and that last digit is going to tell us the number of valence electrons. And that's it, so it's 5. It's also a member of group 15, which could help to answer that question? They're just pulling random numbers from the nitrogen box. 7's the atomic number, 14's the mass. It's important to be careful. 34. I would say this is the question, or rather the vocab term that most teachers actually don't teach you. That is allotrope. Allotropes are different arrangements of atoms in an element. So a lot of the time they talk about graphite and carbon, which is what's happening here. Graphite and diamond are both solid forms of the element carbon. Which statement explains the different properties of these two forms of carbon? So the graphite is going to be bonded in like hexagons, and then those hexagons kind of line up into these thin sheets. So when you write with a pencil, the sheets just like shave off the pencil. And in diamond, they're kind of like interlocked, and that's why diamonds are super strong. For the other option is oxygen and ozone, O2 and O3. Those are the ones that they talk about all the time. Really what it is that you have atoms of carbon or atoms of nitrogen, and they're just bonding to each other in different structures. And that's it. And the structure is going to dictate the properties. Whoa. So diamond does not have ionic bonding. If it's ionic bonding, then it would have to have a metal in there, or a positive ion. Diamond has metallic bonding. It is not a metal. Diamond has a different crystal structure than graphite. That is the correct answer. And then diamond has carbon with more valence electrons. Then it would have to be ions. I would assume that that's the most common wrong answer, because chemistry is all about electrons, and when in doubt, you choose electrons. 35. Ugh, gross. Percent error. It's our first calculation, though. A measured value for the atomic radius of platinum atoms was determined to be 143 picometers. Based on table S, what's the percent error of the measured value? Okay, so this is kind of like a two-step thing, because we need the percent error equation, which anytime you have to do math, you should be able to find the equation on table T, the back cover. So don't go looking all through the reference table. All of the math is on the back. And for most of us, it's T for terrible. That's why it's table T. Percent error is the measured value minus the accepted, divided by the accepted value times 100. Now, what they don't tell us on the reference table is that this actually is supposed to be an absolute value. In chemistry, positives and negatives are kind of annoying, right? With delta H on the potential energy diagrams, positive means heat is entering, and XO or negative means heat is exiting. On the percent error, a positive percent error means that your answer was bigger than the accepted value, and a negative percent error means that your answer was under the accepted value. So that's technically an absolute value, because we only ever report percent error as a positive. They don't put it on the reference table, and it's like the most frustrating thing. So that's just something to look out for. We need the atomic radius of platinum in order to correctly answer this question. Platinum is PT, and I don't remember the atomic number. Platinum. I know it's a transition metal, and it's somewhere near gold. Is it right next to gold? Yes, it is. Platinum is number 78. And what is this first column? First ionization energy, atomic radius. Okay, so the atomic radius of platinum is 130 picometers. I always want to say picometers. 130. Okay. We're doing measured minus accepted divided by accepted times 100. The measured value was 143. Yowzers. 143. The accepted value is the one that comes from table S. That's the one that the scientists say, hey, that's the answer. And then we'll just multiply that by 100. Okay, so really the important thing there is getting the accepted value in the denominator. 13 over 130 is 0.1 times 100 is 10%. Okay, so that 13 is the wrong answer. And that wrong answer is going to come from some kid just subtracting those two numbers. The 0.10 is for the kid who forgets to multiply by 100. And the 9.1 is probably putting the wrong number in the denominator. Yep. So just be careful with that. And that's that. The chemical formula for sodium oxalate. Oxalate, ATE, tells me that I probably have a polyatomic ion in my compound. And we do, because oxalate is a poly. But it doesn't come up often, so even I haven't memorized it. Oxalate, right here. C2O4 with a -2 charge. I'm just going to crisscross those. Sodium is a member of group 1. If we look it up on the periodic table, it has a +1 charge. And then we have the oxalate ion, which is C2O4 with a -2 charge. The important thing here is to realize that when you crisscross, specifically with a poly, you have to take the number and take it all the way across the bundle. And this one comes all the way across the bundle. And we are going to get Na2C2O4. No need for parentheses because the sodium crisscrossed a 1 over here. That's going to leave us with choice 4. Okay, moving right along. 37. Given the formula of a compound, what's the molecular formula? I wish they would say given the structural formula of a compound. We have 3 carbons. Wow, you just had to count. There's 3 carbons and 6 hydrogens, and that's it. The molecular formula is the real formula, whatever you're looking at, the formula of that. The empirical formula is when you go and reduce it down to the skeleton, like you take all the subscripts and you reduce the heck out of them to figure out the basic ratio of one element to the next. And that would have been choice 2 if it asked for empirical, but it didn't. Just asked for molecular, which is the one right in front of you. If you don't know the vocab, you would get that one wrong, but otherwise it's a very easy question. 38 asks, which equation represents a conservation of charge? Conservation of charge means that we are looking for the same number of electrons, really, on both sides. Or the better way to do it is that the reactant's charge is equal to the product's charge. So kind of looking at this, choice 1 here has 1 negative on the iodine, but then it has 2 negatives on the electrons. So in total, that is -3. And iodine, elements that are in their natural state, like iodine being diatomic, are going to have a charge of 0. So -3 is not equal to 0, so that's not conserved. Choice 2, we have obviously -2 in those 2 iodines. And then over here, we have iodine with a 0 and -2 on those electrons. So I'm going to guess that this is the correct answer, but I'm going to do the others for the sake of learning. Over here, we have bromine, the element, which is 0. And then we have 2 negatives between the 2 bromine ions and 2 negatives in the 2 electrons, which is going to, in total, give us -4. 0 is not equal to -4. Then we have a bromine atom, which doesn't ever happen, and 2 negative electrons, giving me -2. But then I have a bromine ion at -1, and those are not equal to each other. So that's how you would figure out that one. 39 is asking which is a single replacement. Choice 1 is a synthesis, where you take the aluminum and the chlorine and you just kind of smush them together. Synthesis is the smush, so that's out. Number 2, we have a single aluminum kicking hydrogen out and saying, hey, that chlorine belongs to me now. And that's the answer. The single replacement is the steel. Choice 3 is a decomposition. We have aluminum chloride breaking apart into aluminum and chlorine. So that's the decomp. And then finally, the last one is the double replacement. We have aluminum breaking apart from the chlorine and pairing up with the hydroxide. Then the potassium is going to pair up with the chlorine, and that's the swap. And that's the double replacement. Now moving into 40. Of course, feel free to ask questions at any time. The bond between which 2 atoms is the most polar? Okay, I already know which one's the least polar. That's fluorine bonded to itself. They each have an electronegativity of 4.0, and 4.0 minus 4.0 tells me that fluorine is a nonpolar bond right there. In order to figure out the polarity here, you're going to use BEND, which is the bond electronegativity difference. You just find the electronegativities and subtract them. My bet is that it's hydrogen and oxygen, but we can still go check on it because truthfully, I'm not 100% certain. Also, I would hate to just tell you the wrong thing based on not looking it up. Okay, so carbon is 2.6. I'm just like right here, 2.6 on the carbon. So this one, oh, I want to write this. Oop. 2.6, and then oxygen is 3.4. Truthfully, it doesn't matter which direction I subtract these, but that should give us 0.8, right? 3.4 minus 2.6. I'm not good at mental math, so I always check. Okay, in total, the difference there is 0.8. Now this oxygen will still be the 3.4. Hydrogen is 2.2. This hydrogen would be 2.2. And while we're here, the nitrogen is 3.0. Okay, so 3.4 minus 2.2 would give us 1.2 as the difference between the two electronegativities. And then 3 and 2.2 is definitely 0.8. So also either of those couldn't be answer choices because they came out to the same answer. So like I said, hydrogen and oxygen is the most polar. (41). The table below shows the volume and temperature of 4 different gas samples at 100 kilopascals. Which 2 gas samples contain equal numbers? Can I explain 38 again? Yeah, I'm going to do that right now. Before I even get into those gases. Okay, 38 is asking specifically about conservation of charge. So what we want to do is make sure that the charges on both sides of the equation are the same, because that's going to give us conservation. The reason it's hard is because it's conservation of charge. All year, you have been doing conservation of matter, where you count, okay, there's 5 oxygens on this side, I need 5 oxygens on that side, and you're counting number of atoms. Here, we want to have the same charge on both sides, and then that's how we're going to figure out if it has conservation of charge. So the also trick here is that when you have an atom or an element in its natural state, the oxidation state is 0. So this iodine coming in as a diatomic will have an oxidation state of 0. This bromine as a diatomic has an oxidation state of 0 because that's how nature made it. And then if we're looking at choice 1 specifically, iodine or iodide ion with a -1 and 2 electrons together will give us a sum of -3, where on the other side of my reaction, my total charge is 0. So somehow I just gained 3 to make this become a 0. So that's not a conservation of charge. Now, if we look at choice 2, we have 2 iodines with a -1 charge. In total, 2 times that -1 is going to give us -2 on that side. On the product side, I have iodine, the element, so that'll have a 0, but it's hanging out with those 2 electrons, and the electrons are in total going to have -2. So because -2 is equal to 0 plus -2, that's why choice 2 is the answer. I'm going to just run through choice 3. If there's questions after this, let me know. Bromine over here is an ion, but I have 2 of them, so that's going to be -2 between the bromines. And then those 2 electrons are also -2. So in total, this entire product side is going to come out to -4, which is not equal to the 0 on the reactant side. So that's also not the answer. There's a slight delay, so I'm going to let you catch up. Let me know if you're good. Awesome. Glad you're good. Okay, 41. The table below shows the volume and temperature of 4 different gas samples at 100 kilopascals. This specifically is asking you about Avogadro's law. Avogadro is that he's got the world's worst portrait. The guy who painted that was absolutely terrible. He's the guy who came up with the mole, and then the mole led to stoichiometry, which kind of stinks. But he said that if you have 2 different gases under the same conditions of temperature and pressure at the same volume, they're going to have the same number of particles. And really all that means is that a hydrogen molecule and a carbon dioxide molecule kind of behave the same so long as they're not reacting, just because they're gases. So he said the identity of a gas doesn't really matter so long as it's not reacting. And that's where the mole comes from. So if we are looking at these 4 gases, helium, neon, argon, and krypton, we're looking for them to have the same temperature, the same volume, and obviously they have the same pressure because that's listed in the question. So it's just a matter of figuring this out. I'm going to go with helium and argon, because helium, we have 1 liter at 25 Celsius, and argon, we have 1 liter at 25 Celsius. So they have the same volume, the same temperature, and they have the same pressure. So they're going to have the same number of atoms. And that's 41. (42) is super annoying because that is Le Chatelier's principles, which nobody enjoys, except for weirdos. Given the equation representing a solution at equilibrium, what occurs when sodium sulfate is added to the system, which increases the concentration of sulfate ions? Okay. There is a trick for this. I have an entire video on Le Chatelier's principles. This one specifically is asking about concentration. And we can follow the rule here, add away, take toward. This will work for Le Chatelier's principles. If you add a bunch of sulfate, which is on the reactant side, I'm sorry, the product side over here, we're increasing the concentration of sulfate, according to this question. So if we add a bunch of product, the reaction goes, ugh, there's a bunch of product here. Break this apart. Let's form some reactants. So in that case, the equilibrium is going to shift away from the sulfate, and it's going to go to the left. The opposite is true. If you were to take out a bunch of sulfate, the reaction goes, wait, where'd all that sulfate go? We got to get that back. And then it will shift toward the thing that you took out. That'll work every time for a concentration. So if we're adding a bunch of sulfate, we're looking for the reaction to shift to the left. And if it shifts left, then the barium sulfate is going to increase as a side effect. And the barium itself will decrease because we're using it up. So that'll be choice 1. The equilibrium is going to shift left because when I add all of that sulfate, the reaction goes, ugh, I got to get rid of this sulfate. So in order to get rid of the sulfate, it has to bond up a bunch of the barium, and then it'll form barium sulfate. So yeah, that one is very difficult. Nobody likes Le Chatelier's principles. But again, I have a whole video on it. You won't have more than one question on Le Chatelier's principles, and you only need 50 to pass. So considering the test is tomorrow, it's time to decide if you need to spend time learning Le Chatelier's principles for 1 point, or if it's better to spend time elsewhere. That's going to be up to you. My advice for it's the day before the test, once this stream is over, read a glossary, which is like so boring, like your vocabulary flashcards if you have those, if not like the dictionary glossary in the back of a textbook, or watch on this channel. Earlier this week I did a stream on the reference tables. Either of those two things are going to be the most beneficial for last minute studying. 43. What is a chemical name for this compound? All right, we are looking at a double bonded oxygen and an NH2 group dangling on the end of this carbon. And those are special simply because they're not carbon and hydrogen. And that's all organic chemistry is. So I am looking for this. Double bonded O with a nitrogen is going to be an amide. And because I have 1, 2, 3, 4 carbons, it would have to be butanamide. Butanoic acid would not have a nitrogen. Butanol would not have a nitrogen. And then butanamine would not have the oxygen. So that one would have to be butanamide. And see, like when you have a question like that, question 42, you're like, okay, whatever, I'm willing to lose it on 42. Because again, most years you only need 50 questions to pass. Okay, 44. Given the potential energy diagram representing a reaction, which interval represents the heat of reaction? This is really like kind of a vocab question. Heat of reaction really means delta H. Delta H is the difference, or on a graph, the distance between the products and the reactants. The products are over here, and the reactants are over here. This is the activation energy, how much energy you need for the reaction to happen. A catalyst is going to provide an alternate reaction pathway. And really, it means that you need less energy for the reaction to happen, so the reaction is easier. Delta H is this section right here. The difference or the distance between the products and the reactants. So that would be arrow 2. 45. Comparing voltaic cells to electrolytic cells, oxidation occurs at the blank. Okay, no matter what cell we're talking about, oxidation is going to occur at the anode and reduction occurs at the cathode. There's a acronym for that. It's anox. Oops. Anox and the red cat. Anox is like a bison type thing. It's an animal. Anode is where oxidation occurs and reduction occurs at the cathode, the red cat. And that again does not depend on the type of electrolytic cell. So that would be choice 1. (46) is fantastic because it tells us use table J. Based on table J, which metal is more active than tin but less active than zinc? Table J gives you symbols. So if the names here are confusing, you just cross-reference them on table S to get the symbols. And here is table J. The cool thing here is that this is listing activity. Tin is annoying. This one is tin right here, SN. It's annoying because it comes from Latin. They discovered tin before the English language existed. ZN is zinc. We're looking for something that's more active than tin. The most active things are towards the top and the least active things are at the bottom. So really we're looking for one of these answers: chromium, iron, cobalt, or nickel. And that's going to be chromium. CR. (47) is going to be a math question. 47 says, in a titration, 10 milliliters of hydrochloric acid is exactly neutralized by 30 milliliters of sodium hydroxide at an unknown concentration. What is the concentration of the KOH? The beautiful thing here is that they actually used the word titration. They don't always do that. We have an equation for that right here. This is that the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. So I'm going to do my math right down here. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Here's my acid. I know it's an acid because the H is in the front. My molarity is that big M. So that's 0.0750 times the 10 milliliters. In this equation, it doesn't matter if you're working with liters or milliliters, just as long as it's the same on both sides. The molarity, the concentration, is what we're looking for. So I'm going to leave M as it is. And then the volume is 30 milliliters. And then you just solve this like algebra. 0.0750 times 10. I'm coming up with 0.75. That's going to be equal to 30M. Next step is to divide both sides by 30 to get M by itself. And 0.75 divided by 30. The molarity I am getting as my final answer is 0.025 molar, which is choice 1. Again, they don't always tell you the number, or rather the They don't always tell you that, hey, this is the titration. Go do the titration formula. It's very nice that they did it here. Okay, number 49. The diagram below represents the bright line spectra of 4 elements and a bright line spectrum produced by an unidentified element. What is the unidentified element? All right, so really we are just matching the lines. So flame tests are not great because flame tests just give you a color, right? You have a sample and you're like, oh, I don't really know what this is. And then you throw it in a fire and then it turns blue. And you're like, okay, well, if it's blue, it could be these 14 different elements. If you use a bright line spectra, then you are going to get the exact wavelengths, and the exact wavelengths are going to be unique for each element. So that's what's happening here. You just need the lines to match. So the unidentified element is going to perfectly match element L, because this line here goes with that line there, this one and this one. They put the measurements on here just so that, like, as you look at them, they like kind of line up. You could also just use your, like, the spine of your reference table to kind of make sure that these line up nicely. If you have any lines that don't, like, even a single line out of place means that your answer is wrong. So be very careful. The other thing that they do is they do mixtures of elements, which we did, I think, on the test yesterday. If it's mixtures, so let's say I just threw X in here. If X were in here, then I would have a line right here and then like a line right there and a line right here and a line right there. This line here would pair with that line there, and every single one of them would have to match. And if there's just one out of place, then it would be no good. Okay, so this was only asking about one element, but if there were a mixture, it would look something like that, and you'd have to line up for 2 of them. Okay, then we're up to nuclear. In the final multiple choice question, it asks, given 2 equation representing reactions, which type of reaction is represented by each of these equations? Okay, well, they're very, very, very different reactions, so it's very fair to say that neither of these are the same thing. They're not the same as each other. So they can't both be fission and they can't both be fusion. This first equation is going to be a fission reaction, and it's fission because we have a big element, and you just kind of like boop, throw a neutron at it. And when that happens, because it's so big, it's super delicate. There's just too much stuff crammed in the nucleus, the uranium's not happy. So it splits into what we call mid-weight elements. Typically, you'll have one in the 50s and one in the 30s, and then you get a bunch of neutrons. And then these neutrons go flying around and hit the other uraniums that haven't reacted yet. So that's fission. Fusion is when you have teeny tiny little elements and they just squish together. So you'd have hydrogens forming helium. You would have a hydrogen and a helium, and they make a lithium. 2 heliums are going to make a lithium. Well, not a lithium. 2 heliums would make a beryllium. Whatever. They're just going to squish together. Fuse. Fusion. They just squish together. So that first one is fission, and the second one is fusion. Okay, before moving on to the free response, is there anything 1 through 50 that I need to go back to? Ooh, I need to stretch. Okay, moving into the free response questions. These sometimes are easier than the multiple choice questions, so don't let that fool you. For the part B's, typically the information that they give you at the front doesn't matter that much, but you should still read it. So I'm going to read them. 4 naturally occurring isotopes of sulfur are S32, 33, 34, and 36. The table below shows atomic masses and percent natural abundance for these isotopes. Okay, so that blurb had nothing to do with question 51 that says state both the number of protons and the number of neutrons in an S33 atom. All right, S33 has 33 things in the nucleus. If we go check out the periodic table, sulfur is in group 16, and it has 16 protons, and those protons live in sulfur's nucleus. Sulfur has 33 things in the nucleus. The things in the nucleus are protons and neutrons. 16 of them, 16 of the 33 are protons. I don't know how many neutrons there are, but I know the total should be 33. So it's just 33 minus 16, and then n comes out to 17. And when you actually answer the question, the answer booklet is going to look something like this. And it's just like a lot of empty space with just lines for you to put your answer. I want you to notice that it just says protons and neutrons. It does not ask you how you figured that out. No one cares how you figured that out. And I'm not saying that to be mean. I'm saying that to kind of like help you out, because every single year that I was grading these tests, most of the years I was actually grading New York City, which would be like kids who were forced to take chemistry and kids who were dying to take chemistry. So you have like the whole spectrum of kids who wants to be there and who doesn't. The kids who really, really, really wanted to like, oh yeah, I know everything, they would explain on the side here, like, I subtracted the number of first, no one cares. Second is that half the time when you over explain, you wind up, because it's a long test and you're already at question 51, you over explain to the point that you throw in one tiny wrong word and now your entire answer is wrong, even though you were like so close. And I was like, oh, you know what you're talking about, but you got this one tiny thing wrong, and on the technicality you just messed it up for yourself. So my advice is to keep your answers as simple as possible. There is no part of this test that says your answer must be in complete sentences. You don't have to write like this is an English test. You're allowed to write like a scientist, chicken scratch, incomplete sentences. Start sentences with because you're allowed to do it. Okay, so take advantage of it. Also, it just, you want to keep your brain from melting because it's a long test. So we're just going to list 16 protons, 17 neutrons, and call it. That's the answer. Okay, then it says, in the space in your answer booklet, show a numerical setup for calculating the atomic mass of sulfur. This one's going to be a hot mess. It's going to be a big hot mess. I'm going to do it right down here. The space in the answer booklet is literally just like a blank space. How you do this is that you take the atomic mass and multiply it by the percent abundance, but percent kind of already is a fraction. 94.99% really means 94.99 out of 100. That's what it means. So you cannot just put 94.99 in an equation, because that's not truly what the number is. So there's two methods here. It depends on if you're math brained or not. The first method is to move the decimal to the left 2 places to turn your percent into a decimal, which a lot of kids like to do. The other option is to just, at the end, divide the entire thing by 100, which would come out to be the same. So isotope 1, I'm going to do in this blue color. You would do 31.972 times, and I'm going to do it like I don't have a math brain because I don't, 94.99. Then I'm going to do the next isotope. I'm going to add that to 32.971.75. The next one will be purple. Plus 33.968 times 4.25. Last one's orange. Plus 35.967 times the 0.01. And then, because it reports it as a percent and you have to unpercent it, you divide the entire thing by 100. If you were to put that in the calculator, what you should get is the mass for sulfur that is on the periodic table. But it doesn't ask you to solve it. It just asks for the setup. So I wouldn't solve it. Because if you solve it and you get it wrong, then whoever's scoring your test might mark you wrong. Just do the setup and walk away. So again, you could preemptively move the decimal if you are the math-brained person who wants to do that. But otherwise, you just just copy mass times abundance plus mass times abundance plus mass times abundance for as many isotopes as you have, and then just divide the whole thing by 100 to get it out of the percent. Then question 53 says compare the energy of an electron in the third shell of a sulfur atom to the energy of the electron in the first shell of the same atom. It wouldn't matter if it was sulfur, chlorine, gold, titanium, or bismuth. If the electron is further away from the nucleus, it has more energy. Think of it like you got your nucleus, and then right next to it you have these electrons, and they don't have a lot of freedom because they're controlled by the attraction of the nucleus. But as your electrons get further and further and further and further away, they are so far away that they don't really feel the nucleus that much, but also there's a bunch of other electrons kind of blocking their attraction. So the further away, the more energy they have. So compare the energy. Here's the answer, keeping it very simple. Compare the energy of the electron in the third shell. I would say third shell electron has more energy. Boom. Keep it simple. Moving on. 54. A student separates a sample of rock salt that has 2 components, sodium chloride and small insoluble rock particles. First, the student thoroughly stirs a sample of rock salt into a sample of water in a flask. The mixture in the flask is filtered using the lab apparatus shown below. Apparatus just means lab materials. It's just fancy science for lab materials. Okay, it says the water is evaporated from the beaker, the filter paper, and its contents are dried. The data collected by the student are shown in the table below. Okay, so we got rocks and salt. And then obviously the salt is dissolved. The salt is going to find its way to the beaker, and the rocks are going to get stuck in the filter paper. And then that beaker, which had water in it, underwent evaporation. So all the water evaporated and it left behind the NaCl salt. State evidence other than mass from the information given that the components of rock salt have different properties. Okay, I would just go with insoluble. Rock particles are insoluble. And beaker with dry NaCl. So it's clear that the water washed the salt into the beaker, but it wasn't able to wash the rocks into the beaker. So it's that NaCl is soluble. So that's the first option. And the second option would be NaCl is small and can pass through the filter paper. Oh, other than mass. Okay. I think those are the only two options. Stirs the rock salt and sample of water in a flask. Yeah, so they're separated. The physical properties that are used to separate them are solubility and particle size, because stuff can get through a filter and filter paper based on particle size. And then 55 kind of gives you the answer to 54. State in terms of particle size why the rock particles are trapped by the filter paper. They are too large. That's why they didn't go through. It's the same with like a coffee filter. If you have like an old school coffee pot, which nobody really has anymore, I guess they're in a Keurig. If you pop open the K-cup, there's like a little like mesh thing in there, and the coffee grounds can't go through, but the coffee water can go through. 56. State the number of significant figures in the mass of the beaker with dry NaCl. Okay, so they're asking you to look at this data right there, 540.0. .0 has a decimal. My decimal is present. So I'm going to approach my number from the Pacific side. I'm going to find my first non-zero number and count everything that comes after it, no matter what. That is going to give me 4 sig figs. There will be probably one question on just counting significant figures. If you don't know them at this point, I wouldn't spend time on it because it's only one question. But if you feel really confident about everything else, there's a video on the channel if you need help with sig figs. Or feel free to ask a question in the chat box, of course. 57. Show a numerical setup for calculating the percent by mass of NaCl in the rock salt sample. I'm curious how the answer key sets this up. Because what you would need to... Why don't they give the... Oh, clean empty beaker. Okay. So what you would have to do is the beaker with the NaCl and subtract the beaker just to find out how much of this mass is salt. So you do 240 minus 224.2, and this would be the mass of salt. And it should be less than 16, but I don't have a math brain, so I'm going to subtract it on my calculator. Okay, I'm getting 15.8. So what you would do is 15.8 over the 16.4, which is the entirety of the sample. And because it's percent by mass, you have to multiply it by 100. You, I'm sure, could also set it up where you do the 240 minus the 224.2 divided by the 16.4, but that has, the top has to go in parentheses. And then you would multiply that by 100. I am going to go check out the answer key for this, though, because I am curious. What they have written. January 2020. Grading guide. This is question 57. .4 minus 0.6. Oh, okay. Why 0.6? Where did that come from? I don't know where the 0.6 comes from. Here, I'll show you what the answers are according to them. They have 240 minus the 22.4. I'm sorry, it's the same numbers. 224.2. Divide that by the 16.4. That's the whole thing. They do 100 times, so the 100 goes in the numerator instead of out to the side. I don't know where the 0.6 comes from, truthfully. What 16.4 minus 0.6 is 15.8. I don't know where the 0.6 is coming from, though. If they say it's an acceptable answer, then it counts. I just have no idea where it comes from. Oh, I guess that's the rocks. But how would you know that that's the rocks? Oh, I see. You would have done the 2.2 minus the 1.6 and got the mass of the rocks. That works too. Okay. My brain doesn't work that way. Okay. So there you have it. They just want the setup. You don't even have to solve it. Oh boy. This looks like it would be a part C question. Cylinders A and B are sealed rigid cylinders with movable pistons. Movable piston is fancy science for the volume can change. Each cylinder contains 500 mils of gas at 101.3 kilopascals and 298 Kelvin. Cylinder A has hydrogen and cylinder B has nitrogen. Compare the mass of the gas in cylinder A to cylinder B. Oh, this is interesting. Okay. So this is a mix of Avogadro's law and kind of molar volume. So we have 500 mils for both of them. They're at the same pressure, 101.3 kilopascals, or as we like to say, kappa. And then the temperature is 298 Kelvin. So they're under identical conditions, meaning that they're going to have the same number of particles / the same number of moles. So let's just say, for the sake of argument, not that this is true by any means, I didn't do the calculation, but we could say that the number of moles for each of these was 2. It's just the same. So let's just say that it's 2 moles for the sake of doing math. 2 moles of hydrogen would be 4 grams. 2 moles of nitrogen would be 28 times 2. Is that 56? Yes. Now, when it says compare, and we're talking about comparing numbers, there are only 3 answer choices. That is, one of them is larger than the other. Well, I guess if one of them is larger, then the rephrase of that is one of them is smaller than the other, or they're equal. So really, there's 2 answer choices. One's bigger than the other, and they're equal. So in this case, the gas in cylinder B has more mass. I would write N2 has more mass. And that would be my answer. They have the same number of particles, but they don't have the same number of grams, because that is why stoichiometry even exists in the first place. Okay, so they say the gas in cylinder A has a smaller mass. The gas in nitrogen has more mass, or hydrogen has less mass. And then you could like copy and paste different parts of these answers to get the whole answer. That's what the but not limited to part means. So that's what that is. I would have said nitrogen has more mass. This, I would assume, is the 100 breaker, as I like to call it. So the 100 breaker is the question where, like, even the best and brightest kids that are like 100s all year long on all of the tests, that's the one that's going to trip them up. I would guess that this is it. I haven't looked at the rest of the test, but that would be my guess. Okay, moving on to 59. State a change in temperature and a change in pressure that would cause the gas in cylinder A to behave more like an ideal gas. Ooh, okay. Ideal gases follow the acronym PLIGHT. That is where their pressure is low. IG is for ideal gas. And then they would need to be under a high temperature. PLIGHT. Pressure low, ideal gas, high temperature. So all we want to do to get a gas to behave more ideally in terms of temperature would be to increase temperature and then decrease the pressure. And obviously a change in volume would change pressure, but they don't ask you about volume, so don't say volume. Just stick with the change in pressure. They ask about volume, the answer volume, but in this case they asked about pressure, so leave it at pressure. 60. Explain in terms of collisions between gas molecules and the walls of the container why pushing the movable piston further into cylinder B at constant temperature would increase the pressure of N2 gas. Okay, so what we're going to do is take the piston and push it down, which is going to squeeze the nitrogen. So what we need to do is, number one, it's already telling us the pressure is going to increase, which is fantastic. So if we're increasing the pressure, it's really just what does that mean for molecule collisions? And I would say molecules collide with each other and the walls of the container more often. Slash with more force. And those would be how I would write the answer. They're doing a very nice thing telling you that the pressure is already increasing. They're saying, hey, the pressure increases. What does that mean about molecule collisions? Pressure is a force of pushing. So they're pushing on the walls of the container. If you have ever played with this, then like you would know. I don't know. There used to be a toy that did something like this. My brain is not working to figure that out right now. Question 61. Show a numerical setup for calculating the volume of the gas in cylinder B at STP. Oh, okay. We're not at STP. We're at 298 Kelvin, which is a little bit warmer than STP. We're already at standard pressure, which is fantastic, but standard temperature is 273 Kelvin. And we're showing a correct numerical setup, which means, hey, we're doing math. But we're not actually doing the math, we're just setting up the math. And we're talking about gases, so it's probably a good idea to check out that combined gas law. The combined gas law is PV over T of the before situation is equal to PV over T of the after situation. In this case, our temperature is already in Kelvin, which is fantastic for us, but it's not always in Kelvin, which is kind of annoying. So sometimes we have to switch that. I don't even have a place where I can write this on this page. I'm going to take it down here. So that equation is PV over T of the before is equal to PV over T of the after. My original pressure is 101.3 kilopascals, and I have this same original, that is standard pressure. So my pressure is staying the same the entire time. It's the same on both sides, so you could plug it in if that makes you happy, but you don't have to. The original volume was at 500 milliliters, and the new volume is what I'm being asked to solve. The original temperature was 298 Kelvin, and the new temperature is going to be 273 Kelvin. So I'm dropping the temperature just for the sake of teaching you right now. If you line up PTV, then you would have kind of like a seesaw here. If the pressure goes up, then the volume has to go down. But if the temperature goes up, right, if this is a seesaw, let's put a little like fulcrum there. If the temperature goes up, then everything has to go up with it because there's no way to make the middle of a seesaw go up. So that would have to be like an indicator of what's happening here. So this is the correct numerical setup. It does not ask you to solve, so you don't have to. I am curious what the answer key says in terms of solving. So am I wrong? Do you have to solve it? $61. Oh, I was looking at 59. 59 was giving numbers. That's why I was confused. So 59, we had to increase the temperature and decrease the pressure, right? Some of these say like specifically to increase it beyond a certain point. Don't give them numbers if they don't ask for numbers. Don't. Because what happens is that you say any temperature above 298, but you actually write 198, or you write it wrong and then you have the wrong answer, even though like in spirit you had the right answer, which really stinks. Okay, so we are getting this right here. Then there are some that are like half solved. You can see that you are allowed to put in the pressure if you choose to, but you don't have to. I didn't because you don't need to. And we're just gonna like draw a little arrow for, that was the ugliest arrow anyone has ever seen in all of time. Okay. Number 62. The electrical conductivity of 3 aqueous solutions was tested at room temperature. A 0.1 molar hydrochloric acid solution conducted, but a 6 molar was a better conductor. Excuse me. A 0.1 glucose solution was tested during the lab activity. Appropriate, blah, blah, blah. Safety equipment. State in terms of concentration of ions why the 6 molar is a better conductor than the 0.1 molar for the hydrochloric acid. The concentration of ions is higher. That's it. There's more mobile ions. So you could do that. You could put more mobile ions in solution. Something to that effect. 63. We had one of these on the last test, too. I think it was the last test. Maybe it was the one before that. The element that allows this to be classified as organic is carbon. Organic chemistry is all about carbon, so that is all you need to know about that. That's the whole thing. Sometimes they're like a little too easy where you're like, wait, was it that easy? I feel like I'm really deep in this test. It should be harder. It's just the way the Regents works. Okay. 64 and 65. Phosphorus 30 and phosphorus 32 are radioisotopes. Phosphorus 30 decays by positron emission. Complete the equation in your answer booklet for the decay of phosphorus 30 by writing a notation for the missing product. I am just going... Whoa. That's not what I want you to do. Stay right there. Give me this. I want just the booklet. I have this set up where I can't write in it because I didn't move it into Cami yet. So I am just going to write it on this page right here. And I just wanted it out on the side. So I get it exactly right. So they provide you with 30 over 15p yields a positron plus blank. Kind of looks like an H. Okay, so when you do this, my recommendation is to set it up like little baby algebra. So I'm going to do the numbers across the top. 30 is equal to 0 plus mystery number. That mystery number would have to be 30. And then across the bottom, we have 15 is equal to positive 1 plus some mystery number. And that mystery number, we're going to make it D. And that would be 14. And then we have to figure out what element has an atomic number of 14. And that would be, I believe it's silicon, but let's just go look it up. It is silicon. Let's rotate. There is silicon with atomic number 14 right there. So we need the symbol Si for number 64. And then, ooh, 65. I love half-life questions. And I think we've had a half-life question on every test that I have streamed this week. So if you need help with that, I think my method's really, really good. But there is certainly a video on the channel if you need help with that. So question 65 is asking to determine the time required for an original 100 milligram sample to decay to only 25 milligrams. So what I do across the top is either the fraction, the percent, the mass. I don't know what else. There was a third option. Maybe I said 3. I don't know. In this case, we're doing mass in milligrams. And then across the bottom, I always do time. And we always start at time equals 0, and we're starting out in this case with a 100 milligram sample. The mass of your sample, or the fraction of your sample, or the percent of your sample is going to get cut in half every single time you go through a half-life. So 100 gets cut in half to 50, and then it'll get cut in half to 25. That's where this question ends, but it would get cut in half again to 12.5, and then 6.25, and then you can go on and on and on. And the time, you are going to add the half-life each jump on this table. So you will add the half-life, and in this case, we only have to add it twice because we're hitting the 25 milligrams. So we have to do this based on table N, and we're looking at phosphorus 32. So we have to pull that up to figure out what the actual half-life is. And these go in order alphabetically by their symbol. Phosphorus 32 is, whoops, we don't care that it's beta negative. We're here for the half-life. That's 14.28 days. Meaning that 14.28 goes here. And then we will add 14.28 again right there. So that would be 28 point something. Or is it 29 point something? 28.57. Oops. 28.57 days would be the answer, because this unit of time is days. And I'm going to take a look at the answer booklet just to see. Oh, they were nice enough. Check that out. 65, they give you the unit, they tell you it's days. So if you accidentally looked at table N and found, I don't know, plutonium, which is working in years, and then the answer booklet tells you that your answer should have been in days, then obviously you know you did something wrong. So that's nice of them. They do that a lot, actually. They give you the units. Okay. I think we have 20 left. Maybe we can do this in 20 minutes. Sir William Ramsay is one scientist credited with identifying the noble gas argon. This is part C also. So they're going to do these things. They're going to give you little stories. They're going to give you like a lot of background information. It applies to stuff in real life, but a lot of the time the questions don't. So don't let the stories like trip you up. Okay, this guy discovered argon. Sir Ramsay separated nitrogen gas from air and then reacted it with an excess of magnesium, producing solid magnesium nitride. However, a small sample of an unreactive gas remained with a density different from the density of the nitrogen gas. Sir Ramsay identified the unreactive gas as argon and then later went on to discover neon, krypton, and xenon. Wow, I'm surprised we don't have an element named after him. Compare the chemical reactivities of nitrogen and argon based on Sir Ramsay's experiment using magnesium. Okay, so nitrogen will react with magnesium, but argon won't. And that's it. That is the whole thing. Where is the answer key? I want to see what they have to say. Yep, the exact same thing I just said. I love when that happens. So this one is like reading comprehension. Like, he didn't even have to know any chemistry in order to answer that one. Isn't that nice from a part C? So nitrogen would react, but argon would not. Done. Compare the density of nitrogen gas to the density of argon gas when both gases are at 298 Kelvin and 101.3 kilopascals. This is a great question because it's just asking you to look at table S, even though it doesn't say to look at table S. And this is why, if you haven't yet, you should go watch my stream on the reference tables. This density has the 2 asterisks right there, And the two asterisks say that we are reporting the density at 298 and 101.3 kilopascals. This is like such a tricky way to do this. I don't love that they did this, but I kind of love it, but also I don't. So we were asked to compare argon and nitrogen. So argon is this one right here, and nitrogen is this one right here. So when it comes to decimals, I will be honest with you, I don't like reading numbers with decimals. I don't know what happened to me in 4th grade. 001145, and then 0. I know I have to line up my decimal points. Mrs. Mitchell did teach me that. I learned long division on a Post-it because I was out sick that day. Maybe that's why I don't like decimals. So when I compare these, especially the densities of gases, what I do is like just go out digit by digit and find out which one's bigger, because obviously they're both super tiny. So these zeros are the same, those are the same, and then these ones are the same. This one I should have labeled nitrogen and then argon. When I get to the 4th digit out, nitrogen has a 1, but argon has a 6. And 6 is bigger than 1, so that means argon is more dense than nitrogen. And that is it. And truthfully, I did this somewhere else in a stream. Like, I do this on the regular, because just looking at those numbers, especially like without rewriting them and just looking at them on the table, like there's a lot going on here. I have to separate it. I am a very visual person. I gotta see it like that. So for this case, argon is more dense. Since I just had a typo, this is not argon. That's element A bonded to element R, and neither of those things exist. So capital A, capital R is made up. If you're a I have to write in capital letters person, then write out the whole name. Some mean person will score you wrong. Okay, state in terms of valence electrons why the noble gases discovered have similar chemical properties. I hope you know at this point, because it comes up all the time when we talk about properties, and especially the periodic table. And that is that if two elements have the same number of valence electrons, they're going to have very similar properties. Chemistry is all about the electrons. Atoms are going to get their personalities and their reactivity, and everything about them and how they, quote, carry themselves is going to be based on the number of valence electrons. So that's really it. They have the same number of valence electrons. And this says specifically state in terms of valence electrons. If you want to get this right, that means you have to talk about valence electrons. Now, sometimes they will accept things like, oh, they all have a full octet of electrons. Sometimes they do, and sometimes they don't. So I would not get cute with it, and I don't mean that to be mean. Outermost shells is synonymous with valence electrons. This one says valence electrons with a complete octet. There's nothing here that does not say valence electron, but says octet. So I would just be super careful with that in particular. Just make sure that you are answering the questions the way that they are asked. In fact, I was watching Hell's Kitchen last night, an old episode, and the chefs are asking each other like, oh, how much time do you have left on this dish? And they were like, oh, I only have one more of them. I only have to make one more chicken breast, whatever. And they're like, no, that's not the question I asked you. I asked you how much time is it going to take, right? It's important to ask questions appropriately as they have been asked. So if this says state in terms of valence electrons, don't go and say they're all members of group 18, because that's true, but it doesn't really answer the question. So just be careful there. 69 says state the trend at standard pressure of the boiling points of these gases as they are considered in order of increasing atomic number. Okay, so specifically the noble gases. Again, I'm going to refer to table S on this. Okay, so let's clear away a little bit of this because now we're talking, what was it, boiling point? Oh my goodness, Cami, you are not friendly today. Goodbye, 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 goodbye. Okay. I just want to check out that test again. It was definitely, whoop, that's the wrong thing. Okay. Booklet. There we go. There's the test. In terms of boiling points, that's what it asked for. So I'm going to check out the boiling points of, oh boy, I need the whole thing here. What did he discover? He discovered argon, neon, krypton, and xenon. Okay, so in order, that would be neon, and then argon, and then krypton, and then xenon. And the question is, what is the trend in their boiling points? The boiling points should be getting higher. Okay, so boiling point is here on the end. I want to look at neon, whose boiling point is 27. Argon is here at 87. 27, 87. Krypton is number 36. Its boiling point is 120. And then xenon is 54, I think, on the periodic table. And the boiling point is 165. And these are all reported in Kelvin. So as the atomic number goes up, the boiling point also goes up. You need more and more energy to boil them. So very simply, it's that boiling point increases. You could say as you go down the group of the periodic table, it increases as you increase the atomic number. All of those would be valid, but the simplest way to write it is just the boiling point increases. Okay, 70. Only 15 more. A sample of normal rainwater has a pH value of 5.6 due to dissolved carbon dioxide gas from the atmosphere. Acid rain is formed when other gases, such as sulfur dioxide, dissolve in rainwater, which can result in lake water with a pH value of 4.6. The equation below represents the reaction of water with SO2. State how many times greater the hydronium ion concentration in the lake water is than that in normal rainwater. Okay, so it's asking us to compare the 4.6 to the 5.6. Rainwater is 5.6 and the lake water is 4.6. Now, we had, I think the same question was yesterday. Not the same question. It was applied differently, but it was the same pH question. If you think back to first grade and you had that number line on your desk and you would use it to count and do your takeaways, right? To subtract. Every jump on that number line was either adding one or subtracting one, depending on the direction that you were going on the number line. pH is a log scale. So you're still looking at that number line, but every single jump on that scale, you have to either multiply by 10 or divide by 10. So the pH scale is looking at 4.6 and 5.6, which would be one entire jump on the scale, right? So pHs that are low are acidic and pHs that are higher are more alkaline or basic. So that's because the pH scale is a negative log scale. Low is high acid. And a high pH is a low pH is very acidic, and a high pH is not very acidic. It's backwards. It's inverted because it's a negative log scale. So because they are one jump away on the pH scale, the lake water is 10 times more acidic or has 10 times the hydronium compared to the rainwater. That would be my answer. Lake water is 10 times more acidic than rainwater. Okay, then it says to state the color of methyl orange in a sample of normal rainwater, which means we need the reference table or indicators. And I did this yesterday. I feel like this reference table could be written better, but it's not. So we have to work with what we have. Rotate, please. Okay, so we're talking about methyl orange in the normal rainwater. The rainwater has the pH of 5.6. I'm going to write it on this reference table. So if we look at methyl orange, let's just draw a pH scale. And we'll put 1 over here and 14 over there, and we'll put 7. And then because we're looking at methyl orange, I'm going to put these two numbers on the scale, 3.1 and 4.4. And then I need to take these colors and plop them on top of the 3.1 and the 4.4. So red pairs with 3.1, and really what that means is that 3.1 and lower, towards 1, would be red. 4.4 pairs with yellow, so 4.4 and higher is going to be yellow. And that means anything in the middle is going to be the mix of red and yellow, which in our case is going to be orange. And they don't really tell you that orange is part of methyl orange. I mean, it's in the name, but it's kind of confusing. And this concept will follow true for all of these, like bromthiamyl blue is yellow if it's 6 or lower, and blue if it's 7.6 or higher, and it'll be green in the middle. You need like your first grade art skills for that. So looking at this beautiful diagram that I've drawn, 5.6 would fall like right about there-ish, whatever. So that would be yellow. So methyl orange would be yellow. And then, we had to have a table G question at some point. Table G, based on table G. Table G. Worst table of them all, because it's such a disaster. What happens to the solubility of SO2 gas as the temperature increases from 10 to 30? Okay, if you already know solubility of gases, you don't even need table G to answer this question, but table G will help you answer this question. We are looking at SO2. This entire graph is on solubility in 100 grams of water, so it's solubility in water. And we're looking at this line only. All of the other lines are garbage. We are looking at this line specifically in the segment from 10 to 30. And we want to know what happens to solubility. And solubility is the line. So obviously, solubility decreases. And that's it. It's going from about 16 grams to, I don't know, 8 grams. I would not say the solubility is cut in half, because if it's not exactly half, then that's like a wrong answer. Just, it decreases. Give them the simplest answer that will actually answer the question. The solubility will decrease. That's because it's a gas. Gases, when it's hot, it's easier for the gas to rise, so it won't stay dissolved. Okay, moving on. A metal worker uses a cutting torch that operates by reacting acetylene gas with oxygen gas, as shown in the unbalanced equation below. That's important to note. And then it asks to write the empirical formula for acetylene. The empirical formula is the most reduced version of the chemical formula, where you take the subscripts and you reduce the heck out of them. And that's just because you want the basic ratio of one atom to the next. So the empirical formula, you take those 2's, C2H2, and you would reduce them. So it would just become CH. And that would be it, because both of the 2's are divisible by 2. In your answer booklet, use the key to draw a particle model diagram to represent the phase of oxygen gas. Okay, well, it's telling you it's a gas, so this is kind of a silly question, honestly. I mean, it's not a silly question for you, because this is a state exam, and you're like, okay, sweet, let me get this. But in terms of like giving this as a test as a teacher, I'm like, this is a really silly question. So I'm just going to copy and paste this thing that comes from the workbook, the answer booklet rather, and throw it down here. And this is what it looks like in the answer book for question 74. And the reason this is important is because if I were giving this question, I would not tell you an oxygen molecule is the double white. I would tell you a single white is an oxygen atom. And I would expect the student to know that O2 means that they're bonded together. So you would have to take the 2 oxygens and put them together. Now, because this is a gas, it should take up the entire container. It should not be organized. It should be very random. Takes up the whole container. That's it. If you were to put them tiny on the bottom, that's a solid. Maybe it's a liquid, depending on how you draw it. That's no good. You want them to take up their entire container. And you have to draw at least 6 of them. And it says 6 molecules. And this double thing is the molecule. So you need 12 atoms in total, giving you the 6 molecules. So just be mindful of that. 75, balance the equation in your answer booklet for the reaction of acetylene and oxygen, which is that up there. We have C2H2 plus O2. Honestly, you're going to rewrite this anyway so that you can spend the time balancing, and then you're going to go put your perfect answer in your answer booklet. So you would do something like this. And some of us can just look at this and like know exactly what we're doing. Others of us are going to do my method, which is where you list all of the elements that you're working with and you count them up. So on the reactant side here, I have 2 carbons, 2 hydrogens, and 2 oxygens. And on my product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. 2 from the carbon dioxide and 1 from the water. And then we have to get everything to be the same. So I will put a 2 out in front of the carbon dioxide. That will fix and give me 2 carbons. It will also change the number of oxygens. So I have 4 within the carbon dioxide plus 1 from the water, giving me 5 in total. In order to get 5 oxygens on this side, I would have to put a decimal, because no whole number times 5 or times 2 will give me 5. So when this happens, the trick is to just double everything, meaning that what I really want to do here is put a 2.5. 2.5 times 2 will give me the 5 that I need. So if I double everything, that'll get rid of that 2.5 that I want to write. So I can put a 2 here. 2.5 times 2 would give me 5. This 2 times 2 would give me 4. And then I would put a 2 right there. So in orange, we can just like recount them. 2 times 2 will give me 4 carbons. 2 times 2 will give me 4 hydrogens. And then oxygens is 5 times 2, giving me 10. Then on the product side, 4 times the imaginary 1 on the carbon in carbon dioxide is 4. The hydrogen is big 2 times little 2, giving me 4. And then oxygen here is 4 times 2, so 8 in the carbon dioxide, and 2 times imaginary 1 in water, giving me 2. 8 plus the 2 is 10. So there you have that. It would be 2, 5, 4, 2 as the coefficients. That's not what it asks for, but that's just for the sake of anybody who's not watching live. Determine the mass of 25 moles of acetylene, and then it tells you the gram formula mass, or the molar mass is 26 grams per mole. So there's a few ways to figure this out. I like to set up a ratio every time, which really for me is talking myself through it. So I always take what's given in the question and put that on top. 25 moles of acetylene is equal to X number of grams. I don't know. But I do know when I have 1 mole of this stuff, it will have a mass of 26 grams. And then I just cross multiply. The reason I like this is because it works all the time. The talking to myself, it just works for my brain. Some of you will look at this and will want to go use table T, and that's just fine. In table T, it's in the mole calculation, so you would take the given mass of 25 and divide that by the formula mass. Oh no, that's not right. You would do 25 is equal to X over 26. That's what you would do. So that's the option there, but I like the ratio method, like the crisscross talking to myself. I know you get the exact same thing. It's like that over 1. I understand. It's just when I talk it out, I understand what's going on a little bit better. So it's the process I've used for the whole year. So when you cross multiply, this would be 1 times X and 25 times 26. 1X is just X. And then 25 times 26 is, I don't know, 650. Sounds good to me. And this is a mass, so that's coming out in grams. Finally, it says for 77, explain in terms of bonding why the hydrocarbon gas used in the cutting torch is classified as an alkyne. Remember the formula for acetylene was C2H2? So C2H2, if you drew it, would have to look like this in order for the carbons to get all of their proper 4 bonds. It tells you it's an alkyne. And then also you have table R, not R, Q. Table Q has that formula for what makes something an alkyne. N also stands for the number of carbons. You can see right there. So if I have 1 carbon, or rather 2 carbons in acetylene, right? C2H2. If I have 2 carbons, then I would be doubling that, giving me 4, but then subtract 2 puts me back at 2. So it follows that formula for an alkyne. But this question says in terms of bonding. So you can't really talk about this formula. It's asking specifically about bonding. So for that reason, we would want the answer to specifically say something about triple bonds. And I'm going to pull up what the key says. Each molecule has a triple carbon-to-carbon bond. The 2 carbons share 6 electrons. Each molecule has a triple bond, and alkynes have a C triple bonded to a C. So all of it is about triple bonds. None of it is allowed to be about that formula because specifically it talks in terms of bonding. So my answer would have been molecule contains a carbon-carbon triple bond. And that would have been my answer for that. And we're almost done. H2O and hexane are commonly used as lab solvents because they have different physical properties and are able to dissolve different types of solutes. Some physical properties of water and hexane are listed on the table below. Compare the thermal energy of a 10-gram sample of water at 25 Celsius to the thermal energy of a 100-gram sample of water at 25 Celsius. Okay, so thermal energy is different from temperature. And thermal, that's not what I want. I want the reference table. Thermal energy is based on mass, where temperature does not matter. So if I have a bigger mass and they're at the same temperature, it contains more thermal energy because it's the energy needed to keep the larger mass hot. That's why all of those Q equations contain the mass component. Right? We have Q is heat, and we have Q equals MC delta T and MHF and MHV. It's not the same thing as temperature. That's why your teacher was such a pain about temperature is average kinetic energy. It's not thermal energy. There are two different types of energy. So thermal, again, is related to mass. And temperature, well, let me write related to. Temperature doesn't care what your mass is. It is based on motion. So it's two different things. They kind of are measuring, like in the real world, they measure similar stuff, thermal energy. Like if it feels hot, it's emitting thermal energy. But if it feels hot, it would also have a high temperature, which is why it's hard for like students to wrap their brains around. It's because they're very similar. But they are different. So thermal energy, the bigger the body, the more thermal energy it has, regardless of temperature. So that is what that question is really getting at. So the larger sample has more thermal energy. And again, when it comes to comparing, they're not asking for an explanation. You don't have to say, because there's a mass they didn't ask. And I appreciate the kids who always want to like share what they know. I really love it. But like, if you get that tiny little piece wrong, then your whole answer is wrong. So just keep it simple, answer the question in the simplest way possible, and move on. And again, there is no part of this test that says that you have to write incomplete sentences. It's not a writing test, it's a science test. So that's why you can write stuff in incomplete sentences. Okay, question 79 says, state what happens to the potential energy of the molecules in a solid sample of hexane at negative 95 Celsius as heat is added until the hexane is completely melted. Okay, so we're starting at negative 95. And it starts out solid. So we're going from solid to liquid, and the question is, what is happening to the potential energy? Okay, potential energy in terms of phase changes is used for pulling molecules apart in endothermic phase changes. So when they absorb energy, the energy is either being used to make particles move faster or to pull them apart. So if we look at like a heating curve, because that's kind of what's happening here, this energy component over time, right? We would start out as a solid, and we heat the solid, and then we melt the solid, and then it's a liquid, and then we heat the liquid, and then we vaporize the liquid, and then now it's a gas, and then we just heat up the gas into the point that we break atoms, which is really, really hot. So this energy obviously is increasing as we go, but this energy is like, we're contributing energy as we go because we're like adding heat the whole time, right? That's fire. During the slanted parts of this graph, we are making the particles move faster. And that is the increase in temperature. So this and this and this, the green sections, are going to be increase in motion and temperature. And on the red parts of the graph, those flat parts, that is where we are going to increase spacing or particle distance. And as a result, we're going to change the phase. And on a cooling curve, those arrows go down. We're decreasing the motion and decreasing the temperature. And on the phase change, we're actually not increasing distance, we're decreasing distance. We're squeezing them together. So the potential energy for melting is going to be used to pull molecules apart or increase particle distance. And that would be it. That's what happens during the phase change. I'm curious what the answer booklet has to say about this, because I don't love this because it starts at, oh no, it's fine, -95. I am still curious though. What do they say? That's the answer booklet. Where's the key? Oh, my answer here technically is wrong because I didn't answer the question, as I've been yelling at everybody to answer the question properly. It says, what happens to potential energy? Not what does potential energy do? My answer was more sophisticated than what the question even asked. Potential energy increases. I'm glad I checked the key and didn't leave you with that. Potential energy increases because we're pulling the particles apart. Apologies. This is what happens at the end of the test. Your brain starts melting, and I have done these all week. Okay, next, determine the vapor pressure of water at 69 degrees Celsius. I don't know that they have to use every reference table, but it looks like on these tests they are using pretty much every reference table, so maybe check them off as you go. Because we haven't used table H yet. Oop, there we go. Table H talks about vapor pressure. Vapor pressure in the simplest terms is how badly a substance wants to evaporate and become a gas. There's a really ugly definition for it. If you Google it, it doesn't really make any sense. Stuff wants to evaporate, and it will, if it has enough heat behind it, or if the vapor pressure is just right. So what we're going to do is check out the temperature of 69 degrees Celsius. Part of the reason I don't like table H is because on the y-axis here, each of these lines goes by tens, but on the x-axis, they go by fives. Not my favorite. So 69 would be right before 70, and that one's 70, so right before it would be 69. And I'm going to scroll up until I hit the line for water and put a data point there. Be super careful with this because ethanol and ethanoic acid, kids confuse them on the test all of the time. So don't be that kid. Take my warning. Now you've been warned. And now you know. Okay, so I'm going to slide this data point over super carefully to the x-axis. And it's actually a little bit lower than this line. So I'm going to say it's like 29 kilopascals. That's what I want my answer to be. I want to see what the range is in the answer booklet. Or rather, the key. Where are we? Okay, so if we look at this, which is how the teachers are going to score it, they are accepting any answer that falls between 28 kilopascals and 30 kilopascals. So if your answer is 31, it's wrong. 29, correct. 28.5, correct. 28, correct. 27.2, incorrect. So there's a range, and they always do this. So, like, don't be paranoid about, oh my goodness, what if I'm off by 0.1? There's a range, and if you are within a reasonable space, which here they have decided is all of 28 and all of 29, up to 30, then that's a correct answer. So don't stress out about those. Okay? Oh, Karen, I'm so sorry I missed your question. Okay, I can't seem to remember matter, what it can be split into, substances, elements, etc. Is there an easy way to memorize them? Unfortunately, there's not really an easy way to memorize them, but I will kind of show you a quick thing. Okay, so we have all of matter. Matter is anything that has mass and volume. I hope you're still here, Karen. I very much apologize for missing your question. Okay, so then we can split this into two categories. The first category would be substances. And then the second category is going to be mixtures. So substances are things that, like, have nice formulas. Those are things that, like, you're gonna find in the chemist's closet. Those are things that, yay, I'm glad you're still here. Those are things that are gonna be in the chemist's closet, and things that, like, they're gonna spend money purchasing. Okay, they're the good stuff. Those are gonna break into elements and compounds. And then we have mixtures, which are going to break into homogeneous or homogeneous, some people pronounce it. And then we also have heterogeneous. So what I like to do is remind myself that elements can come in two different formats. They can come as monatomic, which is most of them. But they can also come as diatomic, which are the Brinkelhoffs, if you remember those. That would be bromine, iodine, nitrogen, Brinkel, chlorine, Hoff, hydrogen, oxygen, and fluorine. Those are the diatomics. Monatomic is literally everything else on the periodic table. So that would be helium, lithium, beryllium, boron, carbon, not nitrogen, not oxygen, not fluorine, but then go over to neon, and then over to sodium, and ... everything except the diatomics. Okay? From there, those are all of the elements. Nature made the diatomics the way that they are. When you have a little bromine floating around in the universe, that bromine will always be paired up with another bromine. Same with iodine, same with nitrogen. Compounds have a definitive, definite formula. So they are going to be things like H2O. They are elements bonded together. Carbon dioxide, CO2. Lithium chloride, a lithium bonded to a chlorine. Then we could have something crazy like a glucose. You have a lot of atoms in here, C6H12O6. If they are bonded together, they are compounds, but they have definitive formulas. So glucose will always be glucose. But then we get into mixtures. And the big difference between substances and mixtures is what they like to annoy us with. Substances are going to come in what they call definite proportion, which means they're always the same all the time. And then the mixtures will come in variable proportion, which means that sometimes they are, like if we look at the homogeneous solution of salt and water. Salt water can be really, really salty, or it could be just a little salty. And that is what the variable part of variable proportion means, is that it changes. So homogeneous would be something like salt and water. When they mix together, they look the same throughout. This is, there's two versions of homo. One is Greek and one is Latin. I think Latin is man and Greek is same. It's same and different. That's what the homo and hetero mean. So homo is the same throughout. Salt and water, when you mix them, the top of the solution is going to look like the bottom of the solution. So a lot of the time you'll see it with that plus sign. This plus that. Other times you'll see it as lithium chloride, and they'll put that little AQ back there. That stands for aqueous. Some people pronounce it aqueous, and that is going to mean, hey, this thing has been mixed with water. And then other times they'll tell you it's a mixture of blank and blank, and it's homogeneous, and you just got to run with it. Now, heterogeneous, I like to describe as having layers. And it makes me feel like Shrek when I say it. What this means is that most of the time you'll see it in solutions. So you'll have a beaker of water, and then it'll become saturated. And you have too much stuff in the solution, and you have extra sitting on the bottom that won't dissolve. And then what happens is that you have a solid layer. So up top, you'll have aqueous stuff. And then on the bottom, you'll have the solid layer. That's how you'll see it in chemistry. When they talk like just strictly like separation of mixtures, the heterogeneous, often they talk about oil and water. Homogeneous liquids would be like alcohol and water, which they use a lot when they talk about distillations. So when it comes to substances, which sometimes they call pure substances, those are the things that the chemists are going to pay top dollar for. They want it to be high quality. When it comes to salt water, that's something that they're going to pay like $1.50 for because they just don't want to make it themselves. So that's kind of the way that I think about it. That's not always like a blanket statement. Is there any acronyms you would recommend learning? Ooh, okay, that is a great question. What is HON 17? HON 17. I don't know that one. BARF has come up on every single test I've done this week, though, so that is great. Let's see. You know what I'm going to do? Give me 1 minute while you answer that question. I have in my Google Drive a file that has like a bunch of things and like common Regents phrases to remember. On 17. Oh, for the diatomics, hydrogen, oxygen, nitrogen, and all of group 17. Interesting. I've never seen it done like that. I've always done it as Brinkelhoff. Let's see. Dictionary of acronyms. That's what I'm looking for. Come on, Google, gimme. Okay, here we go. This is a great thing to stream in the middle of my Regents exam. Let's see. Let's zoom in real good so we can see what's going on here. Okay, so number 1 right here is King Henry drinks unusually delicious chocolate milk, and that is for the metric system. Those are your prefixes. Most of the time, you're just converting between milli and unit, or unit and kilo. That's just so that you move the decimal the right number of places. There's a video on this channel like all about converting metric units. You don't do very much of that though. Then we have the Pacific Atlantic trick for counting significant figures. Pacific is if your decimal is present. You would approach from the Pacific side of the number, find the first non-zero, count it and everything that comes after it to find the number of sig figs. If your decimal is absent, like it's not written in the number, then you would approach from the Atlantic side of the number, find your first non-zero, and count everything that comes after it, but you have to keep counting in the Atlantic direction. And then that'll tell you the number of significant figures. Then we have Brinkelhoff, which is your diatomic elements. Ooh, MELPS. MELPS is a good one. MELPS comes from my chemistry teacher, and it stands for, come on, metals, electrons, lose, positive, and smaller. And I like to say MELPS helps. And really what this means is that when metals lose electrons, they are going to become cations, which are positive ions, and their radius is going to shrink. And then nonmetals are the opposite. Nonmetals are going to gain electrons. They are going to become negative, and they are going to be a little bit bigger when they become ions. Then we have the crisscross rule. Some people call it drop and swap, and that's when you're doing ionic bonding. The weird metals are the transition metals. And they're just weird because we can't predict what their charge is very easily. And they are going to need Roman numerals when you name them. But the normal metals in groups 1 and 2, plus a few others distributed out the table, they have a very predictable oxidation state. So like silver's always +1. Cadmium is always +2. Lithium, always +1. Magnesium, always +2. Those are like the normal metals because they play by nice rules. Then we have the Roman numerals. Oh, you know what? One year they were really, really, really mean, and they asked kids to name or give the formula for vanadium V fluoride. And a bunch of kids thought, because vanadium's symbol is V, that they were asking like, oh, we're just telling you that vanadium is symbol V. But really, that was Roman numeral 5. And if you, depending on the age of your chemistry teacher, they may remember that question being asked. So, just a silly thing. You crisscross the 5, and then chlorine's always a -1. Greek prefixes for naming or covalent molecules different than the organic ones. You have mono, di, tri, tetra, and then the rest of them match the organic stuff, and they'll also match geometry. So that's pent, hex, hept. I'm sure you know the deal at this point. Oh, bend and snap. So bend is when we're talking about polar bonds. That stands for bond electronegativity difference. If you have to figure out if a bond is polar or nonpolar, you just subtract their electronegativities from table S. Snap. If a molecule or if a bond is symmetrical, then it will be nonpolar. If it is asymmetrical, meaning it's not symmetrical, then it will be polar. The steal your girl reaction is a silly thing that my students say, but really it's referencing the single replacement reaction, where you would have something like A is trying to have a reaction, and you have BC there. If A is positive, then it will pair with C. We always write the positive thing first, so it's going to pair up with the negative, which is C. But if A is negative, like if A is a nonmetal, then you would have BA and C, which oftentimes you figure out better in context than you would from the general formula. ADBC is the double replacement. In a double replacement, you'd have something like AB trying to have a reaction with CD, and they swap partners. So A is going to pair up with D every time, and that's because A is positive and C is positive. So A and C don't want to pair up because they're both positive. A is already paired with B, but is trying to have a reaction, so it doesn't want to be with B anymore. Now it wants to be with D. So it's going to give us AD. And then we always write the positive thing first, so CB will be the next pairing. I have a lot of things in here. Way more than I was expecting. Okay, for combustion reactions, when you do a combustion reaction, or a way to assess if you have a combustion reaction, your products, if you list them in order CHO, you should have 1 carbon, 2 hydrogens, and 3 oxygens, because the products are always carbon dioxide and water. And we had a combustion on this test, so I will pull it up. Where's the test? Here it is. Right here. This is a combustion because my products are carbon dioxide and water, CO2 and H2O. And then if we look at how I balanced them, which is really ugly at this point, we can redo it over here. I have 1 carbon, 2 hydrogens, and 3 oxygens, 2 in the carbon dioxide and 1 in the water. So you'll get 1, 2, 3, carbon, hydrogen, oxygen. That's a way to help you identify that you have a combustion. But that's in the unbalanced reaction. If it's balanced, then that doesn't apply anymore, because you may have a different number of carbon dioxides and waters. Okay, double the decimal. I won't do that very much because that was also the process for how I balanced this particular question. So if you scroll back in the timeline to question 75, you can see that I doubled the decimal there. So I'm not going to go through that, but that's the process. The mole always gets the 1 is when you're doing gram and mole conversions. Let's see. I think we did a gram and mole conversion in here somewhere. Yes, we did. Also with acetylene, I think. Where is the test? Yeah, so that was 76. Question 76 is the mole always gets the 1. When you do a mole conversion, it's because you're doing the molar mass, or rather the gram formula mass. So you would have, like, right here, the gram formula mass here is 26 grams is equal to 1 mole. That's the mole always gets the 1. Then molecular is multiplied. That kind of helps when we're talking empirical and molecular formulas, because a lot of kids confuse them because teachers teach them together, and then it's just like it scrambles in your brain. The molecular is the multiplied version, where empirical is the divided version. Plite is one of my favorites. It was on this test as well, but I don't remember where. You'll have an ideal gas if your gas is under low pressure and high temperature. And what that means is that your gas particles are not squeezed close together and they're moving very quickly. And when they're under those conditions, they're not able to feel intermolecular forces, which is how you know that they are behaving by the rules of the kinetic molecular theory. So plight will help you to recognize if your gas is behaving ideally. The PTV scale is pressure, temperature, and volume, which I did somewhere on this test. Let's find that. If you put it like on a seesaw, yeah, right here, PTV. T has to go in the middle. If P goes up, then V would have to go down. If V goes up, P goes down. But if something happens to T, it's going to happen to everything because it's in the middle of the seesaw. So it has to like rise. If the temperature rises, everything has to rise. And if temperature falls, everything has to fall because there's no way to get the middle of the seesaw to just shift one way or the other. The chemistry home run is collision theory and effective collisions. In order to hit a home run in baseball, you have to hit the ball very, very hard, and you have to hit the ball at just the right angle. If you hit it at the top of the bat, it goes flying off foul, and you don't get to run. Kind of only works if you know baseball. Getting on and off the bus is related to equilibrium. 5 people get off the bus, but 5 people get on the bus. The number of people on the bus stays the same. So the concentration or the number of people on the bus stays the same. 22 is related to that. Constant versus equal. Your concentrations will stay constant in chemical equilibrium, where your rates are equal. The forward reaction happens at the same rate as the reverse reaction. And for that reason, 5 people get on and 5 people get off. The numbers stay constant. Leo says GER. Some people use oil rig. That's losing electrons oxidation, gaining electrons reduction. And then you also have oil rig. Oxidation is loss and reduction is gain. I like this one better because it specifically reminds you it's electrons. And sometimes, like on this test somewhere, one of the multiple choice questions, they were talking about moving protons. Leo says GER helps you to remember that it's electrons. The anox and the red cat is really great, but I prefer the red cat gets fat because not only is the anode where oxidation happens and reduction occurs at the cathode, but as your voltaic cell is running, the cathode is going to put on mass and the anode is going to wither away. And when the anode completely withers away, that's when your battery dies. And that question comes up every once in a while, so the red cat gets fat. Cathode puts on mass. It's also putting on mass because it is gaining a bunch of electrons. And as it's gaining electrons, ions from the solution are coming to eat up those electrons. Cathode has a positive T in the front, or rather a bolded T, and that's because in a voltaic cell, the cathode is positive, but also cations are positive. Cat has a plus sign in it. Jack is for table J. I know, I'm running through this very quickly. There's a replay, though. If you need to go back and hear anything, there is the replay. It's going to be available immediately. In fact, you can scroll back right now. Where is table J? It'd be cool if I knew my alphabet. Okay, table J. The most active things, your anodes are going to be at the top, and your cathodes will be at the bottom. So it's Jac, J-A-C. Fusion, like nuclear fusion, is fusing things together, like 2 little hydrogens fuse together and become a helium. And then key phrases that they love to talk about. The sea of mobile electrons, that means metallic bonding every time. Provides an alternate reaction pathway, is a catalyst every time. Allows for the migration of ions, that's the salt bridge in a voltaic cell. And then most of this stuff at the bottom here, I talked about in the Regents stream that I did earlier this week. And it's talking about like what you should do to your reference tables the minute you sit down. Oh, they've changed this. Those are all in Kelvin now. All the temperatures on table S are in Kelvin. I guess they used to be Celsius. But anyways, here it is. If you want to just pause the video and read this, this is what to do with your reference tables. Again, there is a stream where I go over like absolutely everything on reference tables, different types of questions that they ask via reference tables. Oh, something else I like about the periodic table specifically. And I have always used this to make fun of students. Losers on the left. If you look at the periodic table, the losers, i.e. the metals, are on the left side of the periodic table, and they like to lose electrons. So, and the left is like, this is the splitting point, the metalloids right there. These are the losers. And over here we have the gainers. And this is in terms of making ions. Okay, Karen, I hope that helped. I am going to finish the exam, and if there's more questions, feel free to drop them in, but I'm going to keep going with this. I'll answer questions as I get through this. Okay, 81. Explain in terms of molecular polarity why hexane is insoluble in water. Okay, good, Karen, I'm glad. Okay, so solubility, this is that like dissolves like that your teacher probably mentioned 14 times and you had no idea what they were talking about. If something is polar, it will dissolve other polar things, and if something is non-polar, it will dissolve other non-polar things. They don't like to mix with things that are different from them because they're not very nice. So molecular polarity. This is polar or non-polar. So when I answer this question, I have to say the words polar, non-polar, polarity. You're allowed to use like related terms. So here I would say, wow. Water is polar. Hexane is non-polar. And that would be it. If you drew hexane, you would probably draw it in a big straight line, and it's totally symmetrical. That's SNAP. That's one of the acronym things. Symmetrical is non-polar, and asymmetrical is polar. So another thing when it comes to water, and I really like bully my students about this, but like I bully them with love, okay? When it comes to drawing the Lewis structure for water, I always tell them to draw it at a right angle. And this is because when you look at this, you will realize that the molecule is lopsided. You have this big negative area over here, and you have obviously the lack of electrons here makes this a big positive area. And this is how you remember that water is polar. If you draw water in a straight line, which technically is correct on a Lewis structure, it will make you think that water is nonpolar. So we don't want to draw water in a straight line. We want to draw it at a right angle. You can draw it like a 7 or an L or whatever, but you want to make sure that you're trying to help yourself here. Number 82, explain in terms of molecular formulas and structural formulas why 2,2-dimethylbutane is an isomer of hexane. Okay, you don't have to draw the molecule here, but for some kids, drawing the molecule is going to help. So I would immediately pull out my organic tables, like QR, whatever they are. Butane has 4 carbons. So just for the sake of practicing, butane is 4 carbons, all single bonds. I have 2 methyls, and they're on carbons 2 and 2. I always draw mine from left to right when I'm drawing them straight up. So I'm going to put a 1 carbon dangle right there and a 1 carbon dangle right there. And these are methyls, so they're CH3s. And then this would have enough bonds to have 4 bonds on the carbon. And that would be 2,2-dimethylbutane. But it doesn't ask for a picture. It asks for an explanation. And you have to talk about molecular formula and you have to talk about structural formula. So they are isomers. So effectively, they could have told you unicorn pancakes are an isomer of hexane. Tell me why. And that would be all you needed to know. So you would have to say that their molecular formulas are the same, but their structural formulas are different. That would be it. The molecular formula is like the formula. So it would be, for each of them, C6H double it plus 2, 14. They have the same molecular formula, but they are built differently. So in the dimethylbutane, the 2 of the carbons are dangles on a main chain, where in the hexane, all of the carbons are part of the main chain. Okay, and this is the last set, hopefully. Yes. Redox is always towards the end. Redox is not scary, though. Okay, a student constructs an electrochemical cell to decompose water, represented in the diagram below. The water in the electrochemical cell contains a small amount of dissolved sodium sulfate to increase conductivity. 3 equations represent the reactions in each test tube and the overall reaction. Safety protocols are followed. Okay. State the change in oxidation number that occurs for oxygen in the overall reaction. All right. Overall reaction, anytime oxygen is bonded to anything, it has to have a -2. It's the only option. If we go check out the periodic table, rotate this. And zoom in right here. Oxygen's only option is -2. So if it's bonded, it's got a -2. And question 38, I think, one of the multiple choice questions was talking about like conservation of charge. And we were discussing about how anytime you have an element in its natural state, so diatomic oxygen, or if you had like just helium or just lithium, not bonded to anything, just the element, its oxidation state is 0. So the change in oxidation state here is going from -2 to 0. Done. 84, I love this because it literally doesn't matter what they're talking about. Compare the number of electrons lost by oxygen to the number of electrons gained by hydrogen. You know the law of conservation is a real thing. And this also reminds me of question 38. The number of electrons lost has to be equal to the number of electrons gained. Otherwise, they're violating the law of conservation. This is like a scary way to talk to you about balancing equations. They must be the same. Otherwise, something is busted and wrong and you're violating all the laws of nature. Again, when it comes to answering the free response questions, keep your answer as simple as humanly possible. Don't talk about numbers here. The hydrogen gains 2. Don't ask. Or rather, don't answer what they don't ask for. If they don't ask about a number, don't give them a number. Because if you give them the wrong number, then your answer's wrong. So just answer the question the best you can. Okay, finally, question 85. Determine the number of moles of hydrogen gas produced when 0.0004 moles of oxygen gas is produced in the cell by the overall reaction. This is the mole ratio question. It's not at all a redox question, which is why we love it, because ratios are not that bad. If we look at the balanced equation right here, we are asked about hydrogen and oxygen. I'm just going to pull out this little piece right here. If I have 1 mole of oxygen, I am also going to have 2 moles of hydrogen. But the question is, what if I had that many moles of oxygen? 0.0012304 moles of oxygen. How many moles of hydrogen would I have? So when I cross multiply this and solve for x, I'm getting 1x and 2 times that number. 1x is just x. So I'm going to do 0.123. Those were all zeros. 4 times 2. And I'm going to get 0.0008 moles of hydrogen. And that would be the final answer. I am just going to cross-reference that with the answer key to make sure that I did the math right. Yeah. Oh, they also accepted it in scientific notation. Okay. But take a look at this. You see, question 84, I said the number of electrons lost is equal to the ones gained. Same and equal are acceptable answers. Literally one-word answers. Don't go crazy trying to, like, answer in complete sentences. There's no part of this test that says you have to answer in complete sentences. Okay, that's the whole test. I am willing to stick around for like 10-15 minutes. If you have any questions, feel free to drop them in the chat box. Otherwise, I need to go feed my DOG. Surprised he's not in here fussing. Let's see. This is my recommendation for what to do, like the minute you sit down. I'm taking questions now for anybody who has them. Looks like there's no questions. Nothing at all? Okay, I'm gonna give you 10 more seconds. I don't want to ditch you because I'm not coming back. Oh, you have a question. Okay, hit it, Karen. How long does it take to grade the Regents exam? It depends on how many kids are in your school district and how many chemistry teachers there are. So the test is Friday. It's Friday morning, right? I think no, it's the afternoon test. Let's find out. Because they take the bubbles and scan them immediately. But at that point, they only know half of your score, and they're not going to tell you half your score. Schedule. Oop. Yeah, it's the afternoon. And Friday afternoon, your teachers are not staying late to grade that. And then the Monday is a holiday. Yeah. So my guess is that you would have your score like Thursday would be my guess. Um, New York City teachers I know are like they get paid extra to grade after hours because I used to do that. Because they like a teacher in Queens would grade tests from the Bronx. There's like thousands and thousands and thousands of kids. But like when I was working at a smaller high school and you only had like I don't know 200 chemistry students, they went a lot faster. And it also depends on the number of teachers that are there. So I would guess like Thursday. They have to be done by Friday because that's rating day. That's the very last day for teachers to submit the scores. Again, it totally depends. And some schools they tell you you have to wait for your report card. Other teachers like email kids right away. As soon as the score is official, they email everybody. It depends. So happy that I could be helpful. This test is hard. It's very hard. My recommendation, honestly, depending on the type of person you are, there's two ways to take the test. If you're the kid who needs like a confidence boost, start at the beginning, get that atomic theory question done, feel really good about it, and then work through the test. Other people like me gas out and like you're at question 42 and you're like, this is going on forever. For those people, I recommend starting at the back. Do the harder questions first and then work your way to what's easier. All right, if there are no more questions, I'm going to give you my final recommendation for studying for today because you need to get some good rest. You should not be up till like 3 in the morning studying. If you still have your textbook or like vocabulary assignments or like one of the orange workbooks, take a look at the glossary, read that over because a lot of these test questions, if you don't know the vocabulary term, you can't answer the question. So I would do that. And then I would take a look at the stream that I did here on the reference tables because those two things in tandem are going to like really take you to the next level. Watching this stream back might help, but I would recommend those other two things aside from this because at this point, like you got to just be done. All right. And if that's everything, then I am going to sign out and wish you luck. I'm going to give you like 20 seconds to ask me a question. I think that was thunder. What does IUPAC stand for? Okay, that's the International Union of Pure and Applied Chemistry. It just means give the molecule its official name. They're the group of nerds that decided how we were going to name everything. So when it's like, give the IUPAC name for CO2, that means you have to name it carbon dioxide. Just follow the rules. Yeah, sure thing. All right, that's everything. Have a wonderful night. Make sure to get some rest, eat a good breakfast in the morning, and good luck.